A very warm welcome to the National University of Science and Technology, MISIS, here in downtown Moscow. My name is Alan Moore and I'm Director of the International Office of MISIS. Now I'm going to translate that into Russian as well, and I'll try to do it as our people get set up here with the translation. So, меня зовут Alan Moore, и добро пожаловать до NITU MISIS, здесь Moskva. I'm delighted to welcome you to the latest in the series of the UK-Russia even, University Alliance series of forums. Of course, today we're going to discuss with leaders in thought and action the topic Smart Energy Systems for a Sustainable Future. На русском мы будем обсудить сегодня очень важный вопрос, связанный с зеленой энергией и источником развития, потому что, конечно, это очень важно для наше время, наше время и наше будущее тоже. Now, before I begin it, I will give thanks to those involved to getting us on air today and getting us set up today, and for gathering the people who are going to really light up your afternoon, whether you're in the UK or here in Russia. Of course, it's evening time in the east of Russia. I'll thank here our people here in MISIS, the Academic University Writing Centre, the International Office, and of course the Centre for Marketing and Communications, who, as I said, got us on air here today. So я хочу благодарить наши люди здесь в NITU MISIS, кто нам помогает, особенно это Академический письменный центр здесь в MISIS, Nasha Umam и Nasha Umik. And also, this wouldn't be possible without the support and the unwavering support of the British Embassy, the cultural section of the British Embassy here in Moscow, because they really have put in time, effort, and of course funds to make sure that we have this bridge, this dialogue between our two great nations. И, конечно, при поддержке посольства Великобритании здесь в Москве, без этой помощи, этой постоянной помощи, мы не можем строить такой мост между наши две большие нации. Now, in just a moment, we're going to start with a little promo video for MISIS. Of course, it's important because we really do love our university. We know how great we are, and we are truly honoured and delighted to have so many viewers and guests here today. Мы будем начинать с маленький видеоролик, чтобы показать чуть-чуть побольше по наш великолепный вуз. So I will ask our guys to roll it there in just one moment, and I will reappear in just a couple of minutes. Okay? Начинай наш ролик, пожалуйста, коллеги.
They say the world doesn't revolve around you. You've heard that a lot, and also that it is going to be hard, that the future only needs the gifted, and even that you won't succeed. Are they serious? We're certain that every human being is inherently gifted, and it's our job to help them discover their strengths. Because your success is our goal. At the National University of Science and Technology, MISIS, we not only create conditions for obtaining high-quality education, but we also develop your personal and creative potential. We train scientists and engineers of the future, leaders in the digital economy, focusing on comprehensive development and building versatile skills. You all have great potential, and to fulfill that potential, you will have access to participation in high-tech projects, modern laboratories and centers, the best online courses and internships in universities in countries like Germany, France, Spain, the USA and Japan. We partner with over 1,600 leading companies in Russia and around the globe, where our students can find the job of their dreams. We are constantly thinking about how to make your student life even more exciting and bright. At the National University of Science and Technology, MISIS, you will become immersed in science, creativity, and self-development. And we are obsessed with your success.
Okay, I hope you enjoyed those couple of videos just to sort of get things warmed up before we begin our forum proper. We're running slightly behind time, but then again, the way things are moving in the world right now, we have to understand that things change, but we're going to get ahead of the game right now. And I'll say that in Russian for our audience as well, Russian speakers. Надеюсь, что вы очень понравилось вот это пару видеороликов, потому что ну, у нас мы чуть-чуть задержаны сейчас, но скоро будет начинать полностью наш первый спикер. I'm going to just give a very, very short background here to these series of forums and how they began and how they are actually massively helpful in terms of continuing and actually developing a dialogue between the United Kingdom and Russia. Я бы говорю чуть-чуть истории по вот этой нашей серии форумов, потому что это очень важно, чтобы как продолжать диалог и разговор между Великобританией и Россией. Back in the late summer, early autumn of 2020, yes, it was just we're still in pandemic mode. We were given a task to try and formulate what ideas, what we need to put forward, and how to run the forums across the period. The very first one, of course, was here in Nizhny and we were in Nizhny and we were speaking about gender equality, especially in the STEM field. Мы начало конца лета и начало осени 2020 года, ну, на фон пандемии, чтобы подготовиться серии форумов, чтобы объяснить несколько проблем и несколько мест, где мы можем пересекаться с друг другом между Великобританией и Россией. Первый форум был здесь в Нитумисис, где мы обсудили проблем с гендерным неравенством, особенно на STEM, на area STEM. We've had hundreds of speakers, hundreds of thousands of viewers, tens of thousands of viewers, and this is the 5th forum we've held here in Nicis within the series, and we're delighted, of course, to continue to do so. One of the issues that we've always faced is to make sure that everyone gets equal airtime and that we have an open dialogue. And I can say for sure that there has been great dialogue after many of the forums that I can attest to personally between ourselves and universities in the UK, and of course invitations to visit there and back. Now, of course, with the pandemic, that's been quite difficult, but now that restrictions are easing, we have opened up even greater channels of physical communication. We're going to see each other and meet each other. После каждого форума был диалог между институтом здесь в России и в Великобритании. Мы помогали друг другу, чтобы как строить такой канал коммуникации, чтобы помогать друг другу и объяснить. Ну, я могу говорить, что мы объяснили много проблем, что мы встретили здесь в нашей работе и работа в Великобритании тоже. And I'll just say that because I continued a little bit more on in Russian than I was going to say in English. And basically that one of the great things that we found in these forums, in almost every one that's been run here in Nicis, we've hosted here in Nicis, is that the problems we face here in Russia are faced in the UK as well. If it's internationalization, while we are still very early in that stage here, we're still not, progressing on the way that they would have in the UK. We are now learning how to do it better, and in the other way around, we've seen great equality in access to opportunities for women here in Russia. In the UK, they're seeing this and say we can push on further also. На вопрос, как пример, интернационализация, мы еще не на уровне Великобритании, но с опыт и примеров, что мы получили через это форум из Великобритании, мы можем уже делать все лучше. And we're going to start, I'm going to invite up my first guest in just one moment, in about 60 seconds, so that is 1 minute, I guess it is 1 moment in time, to begin our forum proper. So if you forgive me for discussing the background, because again, we've seen events right now moving on our borders and around Europe, and a lot of the time people, when they have a chance to talk and discuss things, they do make things better. The best form of dialogue, in my opinion, and the opinion of many of my colleagues, is through culture and arts, whether it be music, whether it be sport, whether it be theatre, whatever it may be, writing. and academics, because again, academics are working at the same level and they want to try and make things better, not just for themselves and their universities, but for the world in general. And it's very, very important that we continue this dialogue because we can make things better through that. And of course, on that, net the fun, na umne energetica u context ustostal развития, so green energy with sustainable development, is very, very important that now we're going to open up on that today, because with everything that's going on, we need to focus on what we can do together to make the world better. To open up a forum today, I am absolutely delighted to welcome up. He is a professor, a doctor of economics, a member of the Russian Academy of Natural Sciences. He's the head of Energy Analysis and Innovation Center of the ERI RAS, well, it's the Energy Research Institute of the Russian Academy of Sciences. You're really in for treating this because it's a great way to open up our forum today. I'd like to welcome up onto the stage Professor Yuri Plakitkin.
Добрый день.
Нужно наоборот. Черт. Ёлки.
Я уже вооружился. Добрый день, уважаемые коллеги. После таких прекрасных слов ведущего мне предстоит совершенно простая работа доложить свой доклад. Тема моего доклада – закономерности глобального энергоперехода, энергоисточники будущего и предстоящие технологические прорывы.
After this wonderful introduction by the moderator,
я, собственно говоря, выскажу свою личную точку
my job
зрения.
will be very easy. I
то,
will
как
only
будет
have to make my
развиваться
presentation. And in my presentation, I will discuss my perspective on the future of global energy, which stages we will have to go through, and which change in the energy sources we can expect. Whenever I say energy sources, I will mean primary energy sources, coal, nuclear power, wood, and everything that's related to secondary derivative energy sources and energy materials and technologies, I believe will be covered by my colleagues after me. So let's start with the principles of the global energy transition. As a matter of fact, at the moment, there are varying points of view on the future of energy. Some say that we must develop green energy, but others believe that there is still a lot of potential for development in the more conventional sources. Some say that we shouldn't be investing into nuclear power, while others are saying that, no, it is the nuclear energy that has a lot of advantages and benefits for the humankind, for the future. And all these changes, or rather all these different opinions can be explained only through the little knowledge about the global principles in the energy transition and in generally in the development of energy in the world. As a matter of fact, energy has its own regularities or patterns, and the first principle of rule that I would like to discuss today is the global energy transition. Today there are many different opinions about the global energy transition. Some say that it is related to green energy. Others believe that it means decarbonization or migrating to new sources, alternative sources of energy. All of these points of view are correct, but they are only correct to a certain value. In addition to the local energy transitions, there is also the so-called global energy transition. And the global energy transition is a state when global energy will have to be transformed and acquire new properties that it never possessed before. And in order to capture these properties, we can talk about two basic components, two basic parameters of energy sources. The first one is the mass of substance, which is converted into the energy, and the second one is the performance or the effectiveness of material transformation into energy. Is the same as energy density or the calorific value. By multiplying mass by effectiveness or performance, we achieve the a better understanding of the global energy transition. So you can look at the curve here and you will see the per capita consumption of a mass of fuel per one person. And this curve has civilization nature, because you can see here how fuel consumption changed throughout the history of humankind and the civilization. You can see that the per capita consumption was growing and growing all the time, and then around 2008, 2010, this timeline is given on the slide. Growth was arrested, it stabilized first, now it's going down, and the fuel consumption per capita is now declining. Actually, this is a very important insight throughout the development of civilization. We accumulated the fuel mass, and then finally, around 2008, 2010, civilization stopped accumulating the fuel mass, and the whole process was reversed, and per capita consumption, like we said, is now decreasing. And global energy now is on a completely different track, and the world economy is now on a different track in its development. Today, the consumption of the mass of fuel that is being involved in the turnover of the global economy and the efficient management of this energy is becoming the main dominating factor in the development of the world economy. Another important thing to notice here is the peak that is shown here on the slide is the only one throughout the history of humankind. And in this period, in this cycle, at the top of the cycle, we find ourselves today. And probably for this reason, this causes so much uncertainty that exists not only in energy, but also in the economy and even in politics. So this is consumption of the mass of fuel. What about the second parameter, the calorific value, the calorific equivalent, the efficiency of mass transition into energy? And well, after this period, it's supposedly growing, but you can take a look at its own curve. In the last 200 years, the per capita consumption of the mass of fuel went up 26 times, while overall consumption of fuel increased 180 times, while the calorific value or equivalent in the last 200 years grew by a mere 3 times. So basically, it feels that people never thought about intensifying the energy density, and finally we made this transition. We have gone through this breaking point when now the humanity is investing into new sources of energy which have very high calorific equivalence. The next chart demonstrates the changes in the energy picture of the world. And yes, the energy state is changing. Everything that was seen as a benefit in the past after the global transition becomes a downside. Per capita consumption before the transition was growing. After the global transition, it's declining. The mass of fuel was growing. Now we're looking at a decrease. The calorific value, like I said, it was experiencing weak growth. Now we will be looking at very strong growth. Consumption of energy was going up, and now it looks like it will be going down. The type of energy, even the type of energy is changing. In the past, it was big centralized energy. Now we expect to see a more decentralized energy facilities incorporating small generation units. The prices until 2008, the prices were constantly growing. After 2008, they started to go down and to stabilize. The power of market economy is also changing now. In the past, the market power was very high. Now, after the global transition, most likely it will be going down. And the economy is changing, and the politics is changing. All the drama in which we are currently living, to some extent, can also be attributable to the global energy transition. We see how economic criteria are becoming environmental, are becoming geopolitical, anything. The world is changing. It's acquiring a new state, and we cannot forecast the energy trends. We can expect the changes in the energy trends, and we must understand under which circumstances the changes will be happening. And now, how is the global how is this affecting us? On this chart, you can see the global energy transition and its relationship to the local energy transitions. I don't want to go into details, just let me tell you that every local energy transition of the industrial revolutions through which the civilization has gone, the first coal industrial revolution, the second oil-related industrial revolution, then the gas one, and now finally we are living in the time of the fourth industrial revolution, and the first step towards this global energy transition coincides with Industry 4.0, with the fourth industrial revolution. And this is a completely different paradigm for the civilization and for the economy, something that we've never experienced before. Digitalization, smart devices, automation, robotics, cyber-physical systems in production, all of this ensures extremely high labor productivity, and high labor productivity means a completely different structure of the economy. In the past, energy transitions led to higher labor productivity through mechanization of labor. The labor was becoming more mechanical. Now, labor productivity will increase only and exclusively through the development of smart and intelligent systems. So all this is very well, but is this sustainable? What will be the sources of energy to support all this progress? And there is the third rule to which we must now turn, and the rule calls the energy density or calorific equivalence of used energy sources grow steadily until they reach a ceiling.
повышают и повышают средний калорийный эквивалент глобальной энергетики до своего предела. А пределом является...
So once again, the energy sources grow steadily until they reach a ceiling, and the ceiling, the cap, is determined by the Einstein's formula, the E equals mc squared, and this is what our civilization is aiming to. We are aiming to achieve this marginal energy density cap. And once again, this is civilizational growth. It does not depend on the cost of energy sources, nor on the prices on energy resources. It depends on the civilization, and it depends on the fact that the humankind devised civilization, and it's developing civilization, not green energy, nor the Paris Accords are going to affect any tangible impact on this process. Even without this climate change agenda, the energy sources would have continued to change, and the calorific value, the energy density, would be increasing, and the humankind would be still switching to energy sources with higher energy density. And this road, this path, is a one-track path, and it's going upwards. It's going upwards, and that's the only way that it can go. Of course, the climate agenda cannot change the cause of events, but of course it has its impact. Of course, I can't deny the consequences of the climate agenda, because it can either accelerate or decelerate that process. The green agenda today is rushing up the civilization. Go on, climb this curve, reach out to higher energy densities. And for you to understand where we are moving, the calorific value of coal is 0.7. For oil, it's 1.44. For gas, it's 2. For hydrogen, it's 4 units. And solar energy, what we are achieving through solar batteries is 4 to 6 tons of fuel equivalent per ton. 4 units, 6 units. Wind energy, 2-3 units. Of course, we still should be looking at that opportunity as well. It's not a negligible opportunity. So as a result, if we manage to get access to all this energy, then how do we use the energy? We use the energy it's kinetic energy, and it's transformed into the speed, into the movement. It's turning wheels, it's making various machines operate. And the average speed at which the global economy develops, it's those graphs, depends not just on the energy density, it depends not only on the calorific equivalent, but it depends on the square energy density. Can you imagine this? So you double the calorie equivalent in the global economy, and the speed of transition changes 3-4 times. The number of industrial transactions or manufacturing transactions goes down 3-4 times. It means the productivity of labor is improved 3 or 4 times. So it means the game is worth the candle, as we say. The humankind needs new energy technologies in order to increase the labor productivity. So what are these technologies? What are we pursuing? And this question, this illustration answers the question. Philosophically speaking, the humans have always been following the sun. Coal, gas, timber. This is all conserved solar energy.
Вот. Но, наконец, мы перешли сейчас,
But now, finally,
когда мы эти консервы перестаем использовать,
we stop
переходим на
using
потребление энергии.
these preserves, so to say, and we start using solar energy directly. We take solar energy and we start applying it in the global economy. We introduce it into the global economy via solar panels, solar batteries. This is the green path, the green journey to the sun, to the natural sun, to the natural thermonuclear reaction. And the second path is to create an artificial sun on the Earth, and this is the red curve. This is when
К покорению термоядерных
humans are conquering the thermonuclear reaction, thermonuclear fusion, and we start
человечеству,
exploiting the sun here on the Earth.
отвечает пятой закономерности.
So this brings us to rule number 5.
Плотности
Rule number 5 says that there is energy density of the primary sources which strictly corresponds to the frequency of their electromagnetic radiation.
этих источников. Вы видите, что
But you can see here that the calorific equivalent is a function of the radiation frequency, which makes our tasks simpler. There is a classification of electromagnetic waves, energy. Every source of energy, rather, has its own wavelength, it has its own radiation frequency. And knowing how radiation changes, we will know how the sources of energy are changing. You can see here the area of conventional energy, infrared and visible light, then ultraviolet, X-ray, gamma, etc., all the way to cosmic rays. So one way or another, we are transitioning towards the space, the open space, the cosmos. And you can see the differences between these types of emissions. Infrared and visible light, this is where we are, the energy that surrounds us right now. And as the next step of the ladder, from 1 unit of equivalent fuel to 80, for instance. And can you imagine how big the jumps will be for us to make? You can see that we systematize these jumps, these energy jumps or breakthroughs, and we also dated these energy breakthroughs. And again, we see a good correspondence with the past industrial revolutions, and now we're looking at the fourth industrial revolution, which is roughly years 2025, 2035. This is when these new energy breakthroughs will be taking place. And the next thing that is waiting for us around 2050, 2070, the second energy jump, and then towards the end of the 21st century there will be the sixth energy breakthrough, and then the seventh energy breakthrough and the seventh industrial revolution early in the 22nd century. Again, we will be looking at colossal changes in the energy density, therefore tremendous changes in labor productivity. It means that we will be migrating to a completely new level of technology development. The scale of future technological transformation is currently probably inconceivable, but just to give you an idea of the potential scale, we can set a mind experiment. Imagine that today we suddenly find ourselves in 1985, 35 years ago. So what's around us? No PCs, no internet, no mobile communications, no cellular communications. There is nothing. There is nothing to which we are well accustomed today and without which we cannot imagine our lives today. So in 30 years' time, the same will have to happen again. And it will come back with a vengeance, so to say. Why? Because the fourth, or rather, in the past 200 years, we saw 4 energy breakthroughs, and then you see that the whole process speeds up. Actually, the speed doubles. In the next 100 years, we will see another 4 energy jumps. And in conclusion of my presentation, we need to discuss one other thing. Knowing what we know today, we can project the energy density curve into the future. You see that around 2025, 2030, the calorific equivalent will be doubled compared to what we have today. Today it's 1.5, but then it will be 2.5, 3, and then around 2050, 2060, again, we will triple the energy density to be achieved in the next couple of years. The energy equivalent will be 9 to 10. So again, an energy breakthrough. And the first energy breakthrough probably will be related to Industry 4.0, and the second one will be related to the global project Society 5.0. No coal, no oil, no gas will be able, given the calorific values 0.7, 1.4, and 2, will not be able to provide us with the required energy densities, but we can get that out of solar energy, hydrogen, and similar sources. That is why it is extremely important to move in this direction. So what will be the energy sources for us in the future? I will not go into too much details right now. I'll just talk through this slide quickly. You can see here again the correlation between different energy breakthroughs and technologies to be achieved in respective periods of time. 2030-35 probably will start using low orbit solar energy, system of stations that will provide not only energy supply to individual regions of Earth, but they will provide energy to spacecraft, to drones, to be used in the global economy. And in those years, if we follow the second track, also it's possible that we will introduce serial manufacturing of fast neutron reactors, the fast neutron reactors of the second generation with gas cooling. Around 2050, 2070, probably will make more advancements in orbital energy, and the solar generation will be implemented not in the low orbits, not low Earth orbits, but in the geostationary orbit. And probably there will even be energy sources and generation on the lunar surface. In terms of thermonuclear power, most likely in those years we will also see the industrial use of hybrid nuclear thermonuclear power plants. I do not want to discuss subsequent energy cycles because the time is running out, and this is probably the last illustration of the presentation, and it speaks for itself. You know that we believed in the past that global energy consumption will steadily rise forever, but it looks like, again, the estimates are showing that energy consumption will decline due to higher calorific efficiency of the energy sources with higher energy densities. And the energy picture of the world around the year 2050 will look as follows. Gas, from the current 18%, probably will will have a share of 29%. Oil will go down from 33% to about 18%. Coal will lose a lot of market from 29% to 6%. Alternative sources of energy will be used more widely. Their share will increase from the current 14 to 41%, and nuclear sources again will become more prominent in the energy landscape. Again, we were pressed for time, and I discussed only 5 or 6 of the principles of energy transition that I hope you now understand much better. Actually, there are more rules to this process. They were listed on the slide. Thank you very much for your attention. And of course, that's not the end of this discussion, because we are always looking ahead and trying to understand what is going to happen in the future. Thank you very much for this presentation. Again, we do not have much time, but still I need to ask you this question. Do you think that nuclear energy is green energy? It's clean, isn't it? Does it make it green? Well, it's difficult for me to answer this question. Whether nuclear energy is green, I understand that there is also a political component to this discussion. I am not a very politicized person myself, so my answer to your question is I believe in the good future for nuclear energy. Why? Because again, for humankind, there are 2 possible paths into the future. And one of them is create an artificial sun on the Earth. You cannot bypass nuclear. Well, thermonuclear is absolutely. This is a type of energy that is definitely very clean. So, in order for us to get to this destination, whether we like it or not, we will have to go through the nuclear cycle first. We can't bypass it. The more we understand it, the more reliable it becomes, and the greener, the cleaner this energy becomes. It depends on the genesis, it depends on how you derive energy. Thank you very much. Thank you. We hope you
so thank you
for the panel discussion.
Yuri Plakitkin for a terrific presentation. We're going to move very quickly across Europe and across to the UK and the University of Cambridge, and we're delighted to welcome on a little bit later than we planned, but they're here anyway. So the Professor of Device and Energy Materials at the Department of Materials Science and Metallurgy at the University of Cambridge. Also Associate Editor of Applied Materials Today. Delighted to welcome on Sohini Karnarayan.
Thank you very much for the warm welcome. Greetings from all the way in Cambridge. So I'd like to share my presentation, but I think I need permission to do so, if the host would. Please allow me.
Guys, can we, yeah? Sohini, it's okay now?
Nope, it still says host disabled participant screen sharing.
Can you try again?
Yep, all right, all good.
It should be working.
We're getting there. Can you see my screen?
It's, we can see it loud and clear.
Brilliant. Sorry, just give me a second. Okay, brilliant. Hi everyone, my name is Sohini Karnarayan from the University of Cambridge. I would of course like to start by thanking the organizers for inviting me to give this talk. Sorry? Is everything okay?
Yeah, everything is fine. So Sohini, it was just a little mix up here with my microphone. Everything is perfectly good.
Okay, sorry. So just to say, thank you to the organizers for giving me this opportunity to present some of my group's work on energy materials in general. So I lead an interdisciplinary research group that works at the interface of material science, device, energy, and also biomedical applications. So here's a very recent picture of my fantastic group. This was actually the first time we were able to get together in over 18 months due to COVID. Pandemic, of course, has brought about challenges and difficulties for all, but thankfully we've managed to keep going on. So just a very quick overview about the work we do in my group here in Cambridge. So we work on developing functional nanomaterials for a range of functional devices. And by functional, I mean materials, by functional materials, I mean materials that are responsive, that are smart, that can respond to changes in the environment, that can respond to heat or to vibrations, and importantly, that can produce electricity at the other end. So here at the top, for instance, you will notice that we do quite a lot of work on mechanical energy harvesting and thermal energy harvesting. And the idea here is that we use these materials to tap into ambient vibrations and heat to produce electricity that can run devices. In this context, we're also looking at sort of modern day electronics, so we need to make these devices flexible and stretchable, and we use various advanced printing techniques, various additive manufacturing techniques, as I believe this is one of the ways forward for manufacturing in general, to convert these materials that we work into devices. And of course, I'm not going to touch on the sort of bio aspects for today, but needless to say, these are all interconnected. What I will say, though, that we do work extensively on materials at the nanoscale, because this is really the scale at which we can manipulate the properties of these materials. And so we do a lot of scanning probe microscopy to understand the properties of materials at the nanoscale, which are quite different from what they would be in the bulk. So with that, for today's talk, this is my motivation slide. So we're all familiar with devices that run on batteries, and your mobile phones, your laptops, and you would know of the inevitable need to replace or recharge batteries to keep your devices running. This is particularly a problem for devices such as wireless sensors that may be embedded within structures or implanted in the body, or basically in hard to reach places. And a lot of these wireless sensors are geared towards the Internet of Things. So in today's forum, you will hear a lot about, and we have heard about, sort of the energy problem from a global perspective. When we think of energy, we often think about energy to light up entire cities. But there is another aspect to this which I'm quite passionate about, which is to make the most of the energy that is available to us, to make the most of our resources. To invest more in keeping infrastructure, for instance, running, to have sensors that can monitor infrastructure before things collapse. So to be able to effectively monitor what we already have and to make better use of the energy that we already have, we would be reliant. We are to a large extent, and this will only become more pronounced in the future. We'll be reliant on sensors that can monitor these, the health and of these. Of our environment in general. And so for this, how would these sensors run? So how do we power the Internet of Things? So this vast network of sensors that are meant to make our lives more seamless, energy efficient, and less resource intensive. So as we mentioned, batteries, of course, a lot of these devices do run on batteries, but then we're left with the problem of recharging or replacing them when they inevitably run out of juice. And this is inconvenient. A lot of these devices could be inaccessible even. And so we could turn to the environment within which these sensors operate to find ambient energy sources. And I often ask this question in my undergraduate lectures, which is, when you think about the environment, the energy available, what do you think of? And people normally would start with the sun, which is, of course, it's an abundant source of clean energy. But for a lot of these sort of embedded sensors, or these sensors which are, as I said, in hard to reach places, the sun is probably not always the most convenient or accessible option. And of course, if you live in the UK, as I do, it depends very much on weather conditions and of course the time of the year. So I've been quite interested in looking at mechanical energy harvesting from ambient vibrations. And this to me is quite attractive because you are never too far from something that moves or vibrates. We also look at into harvesting waste heat energy as well. But in today's in today's talk, I'm going to concentrate on mechanical energy harvesting. And as we're discussing smart energy systems for a sustainable future, I thought I'd just include a brief slide about some of the work we do in the area of remote health monitoring. So we're looking to deliver point-of-care devices that rely on electrical signals arising from biological processes. And these could potentially be self-powered through energy harvested from body movement itself. So in other words, devices that can monitor physiological signals in real time via skin-based or home-use sensors and these could improve clinical outcome and, importantly, reduce the burden on healthcare systems. And a major bottleneck at the moment is how to power these sensors, and the answer may lie in the mechanical energy of the body itself. So in this context, let me quickly jump into what are known as triboelectric generators. So again, some of the audience may already be familiar with this, but maybe others not so much. This is actually a kind of energy harvesting technology that's only been around for the past few years. Really, I think 2012 was when the first ones came into being. So the effect actually is an effect we've known for more than 2,000 years, and that is if you have two dissimilar materials, you rub them against each other, there is some charge transfer that takes place. And we commonly know this as static. When you get a shock when you touch a brass doorknob, say on a cold day. So in this video, we're going to harness this sort of rubbing or static electricity. So here we have two materials that are being rubbed against each other. The electricity that's being produced is stored in a capacitor, and then when we discharge the switch, we can light up some LEDs. There are different ways that you can do this. You can either rub the materials together, or you can just essentially, make and break contact. So this is another very simple version. Here are two different materials, Kapton and copper, and we have a bank of LEDs. And you will see that if you just directly connect these materials to our bank of LEDs, then just by simple simply tapping, you can produce a finite amount of electricity that can be used to light up LEDs. Of course, this is still a bulky object. We want to be able to make these much smaller, much more efficient. And so here we have an experiment doing pretty much the exact same thing, but you'll see in a second what we're actually using are polymer nanowires to generate all of this electricity. And the reason that we're able to do this is because we're able to manipulate the materials. So I'm coming to this forum sort of from the angle of materials. Materials as being sort of the underpinning, almost a cornerstone of these technologies, these brilliant technologies that can really change our lives. So the triboelectric effect, as I mentioned, is where you rub two dissimilar materials and charge transfer takes place. And this can be harnessed to then power devices. Now, there is an empirical triboelectric series. So basically, this is a series listing materials in terms of their tendency to donate, accept electrons. And ideally, you want to focus on the extreme ends of this series. So you want to bring materials which are very tribopositive and very tribonegative and bring these together to have the maximum charge transfer. Unfortunately, if you look at this series for a little while, a lot of the tribonegative materials are indeed polymers, synthetic polymers that we can make in the lab. But on the other end, we've got things like skin and hair, which aren't quite what we want to work with. And so in my group and in research groups around the world that are working in this area, we're looking to develop more tribopositive materials, but also we're looking at ways by which we can improve the performance of these devices. So we're looking at ways by which we can functionalize these different materials to increase the surface charge, because at the end of the day, it is the surface charge that is being sort of moved back and forth. So we do this in a variety of ways. We published a nice review article that looks at some of the ways that are currently available. You can inject charge directly onto surfaces. You can functionalize the surface, so you can put in molecules onto the surface of materials, which make them have a higher surface charge density. Or you can work with what are known as ferroelectric materials that have an inherent polarization. So they inherently have a large surface charge present that can be harnessed. And just a quick example of kind of the way we manipulate these materials. So these ferroelectric polymers, so these are materials that have an inherent polarization, have an inherent surface charge. But this ferroelectricity is rooted in the crystalline structure of these materials, which is not always to control, particularly when it comes to, organic materials or polymers, unless, as we found, you work at the nanoscale, where not only can you control the crystallinity of these polymers, but also their phase. So in this example, PVDF is a very well-known ferroelectric polymer, but it occurs in different phases, and only one of these phases, which is commonly known as the beta phase, will give you this polarization that you want for your triboelectric effect. And what we found is by manipulating the way we make these materials, particularly at the nanoscale, we can manipulate very nicely the crystallinity and the phase of the material present. So there are different ways to do this. You can use methods such as template wetting, electrospinning, nanoimprinting. Of these, our group has pioneered this first one a fair bit, which is template wetting, where you grow nanowires within molds. For instance, we use this to show that nylons, which you will be familiar with, in textiles, these are actually highly tribopositive materials, but they haven't quite, they were reported in the literature, but were mostly abandoned as their properties were quite poor. But we sort of revived these using our materials fabrication and the ways we manipulate the structure really at the nanoscale. And so I won't spend too much time on this, but just wanted to quickly say that we now have precise control of phase and piezoelectric or even triboelectric properties in these sort of nylon nanowires, which is great because this is a material that lends itself quite well to smart textiles. So we produced, for instance, these triboelectric yarns. So essentially there's a conducting core, which is based of carbon nanotubes, and we've electrospun various polymeric nanowires onto the surface. So we really have yarns which can then be woven together into clothing. So just going back to some of the applications I was talking about, particularly in medical applications, where you could have clothing that is able to harvest some of your body mechanical energy and power, say, an implanted device or a device that is monitoring physiological parameters, which doesn't require you to go to a hospital and which can lead to personalized medicine, which means that our healthcare systems can function better, because this is all part of the sustainable picture. So just over the years, we've if anyone's interested, we've published quite a few review articles in this area, lots of fascinating material science and engineering in this field, and if you're interested, these are very good reference points. So I just wanted to kind of end by end my presentation here by talking about a term which has been coined, and this is blue energy harvesting. So we hear of green energy, and this term was coined not by myself, but this term was coined, and it's called blue energy. And this is where we can use these sort of triboelectric nanogenerators to harvest energy within our ocean systems. And this could be both in terms of wave energy, but also wind energy associated with these regions. Usually the kind of generators that are typically used to harness this energy are electromagnetic generators, but these have a lot of issues, especially when it comes to low frequencies that you would typically get from waves. And so Professor Zedelwang has really been the pioneer in this field. He's done a lot of work and inspired a lot of research groups around the world to look into blue energy harvesting for powering, for instance, sensors within the ocean. But the bigger picture is perhaps, if we are able to develop the right materials, the right tools, to make sure that these materials can survive, over long periods of time, then this can go beyond just, the realm of sensors and wireless networks. But as I'm sure you will hear in many of the talks that follow, the materials are one aspect of it. So the design of the energy harvesters are just one aspect of it. There's a lot more that goes in terms of the networking strategies, how these sensors talk to each other, the power management, and also, of course, the application system itself. And I'm sure there'll be quite a lot of discussion about this that follows. But I just wanted to sort of end on this slide just to say that these materials really are going to underpin some of these technologies that will come about in a big way in the future. So I just wanted to really present kind of the materials case and the need for advanced materials research into advanced materials across the board. So with that, I'm going to end the presentation. Once again, thank you very much for your attention.
Microphone. Sohini, thank you very, very much for an excellent presentation. Very enjoyable, and it does look like you're getting lots of sunshine there behind you in the UK at the moment.
Indeed, today is one of those days. But we also, I don't know if you might have heard in the news, we've been battered by 3 storms back to back, so we're also feeling the after effects of that. But again,
I've seen them, yeah. The storms are pretty. I mean, if you're talking about like sustainable energy, I mean, you would have had wind,
yes,
power, wave power. It was definitely online. So, I have just a couple of questions for you, just from some of our viewers. First one, I'm going to go to the Russian State Social University, Professor Sergei Ivanov, and his question was, From all of this, how do you see that people can, businesses can make money from this?
So an excellent question, because we do work with industry quite closely in order to develop some of these technologies. I think the main issue for this type of technology is whether it will outperform or outlive the current technologies that exist out there. So we do rely on batteries for a lot of these applications, but batteries are cheap. They're not necessarily, as these networks expand, I don't think that this will be a sustainable way to go forward. So really, it is to convince industry to invest in this type of technology, because it's only then that you can drive the prices of some of these materials down. Because, like I said, in order to get the best performance, you have to be working at the nanoscale. You have to be able to scale up. So these are currently the challenges, I believe, and also to show that it outlives the current solutions that are out there. And again, because I am from a material science department, I always push materials forward. The more advanced materials that you can come up with, the more functionalized these materials can become, they will perform better. And so it is trying to convince industry that it's worth the investment for a payout later on.
Okay, no, that does make perfect sense. Like, the longer the life, the better it's going to work out. And just on that, in terms of with the batteries, there's a great question coming from Yelena Chernysheва. She's an editor with fb.ru. It's an education blog, and she said, "What are the perspectives for such programs in higher education?"
So again, a great question. I believe this offers opportunities to to undergrads, to graduate students, etc., to think slightly outside the box, and to think about, we always have this idea, as I said in the beginning, of energy being this sort of global scale problem, which it is. But there are things that we can work on, which make our use of energy more efficient. And I think it's important to look at both ends of that spectrum. And so for people coming into higher education, just sort of trying to change the perspective slightly a little bit, just to think about, other solutions that might exist out there that could actually, if not alleviate completely, but definitely help with the current situation. I think is a good thing. And again, this focus on materials and these new technologies that are at our fingertips, which we didn't really have. Like I said, this particular effect we've known for more than 2,000 years. So the question is, why is this relevant now? The reason it's relevant now is, one, we are able to make better materials, we're able to make better devices, but also the power requirements for a lot of these have gone down. So there's a lot of work in engineering and electronics, on that side of things, where the power requirement of these sensors has been reduced to such an extent that it is now feasible to think of powering them from ambient energy. So in that sense, I think there's like a lot of scope for development and for people who sort of coming up, who are interested in research and development and in process engineering. This is definitely a very, I would say, attractive field. If that answers the question.
Answers it in depth and perfectly. Thank you so much to the Professor of Device and Energy Metals at the Department of Material Science and Metallurgy at the University of Cambridge, Professor Sohini Karanarayan. Thank you very much for your time today.
Thank you.
Okay, and folks, we will move now. Well, we're going to stay actually in the UK right now. So the weather is an awful lot better. It is a calm after the storm. And we're going to go to the University College London and to the Professor of Energy and Environment at the Bartlett School of Environment, Energy and Resources, the Faculty of Built Environment, the Energy Institute. Would like to welcome on Dr. Taj Oreshin, and I hope I pronounced that correctly.
That's great. Thank you very much. Can you hear me and see me?
Well, I can hear you loud and clear. I can't see it just yet, but our experts here are oh, now we see it perfectly well, and a lovely white background and sun in the sky.
Okay, and I'm just going to try and share my screen.
Now, just as your screen is coming up there, and of course, your presentation is on buildings, smart meters, and the net zero transition.
Can you see this full screen?
Yeah, we can see it now. We can see your presentation.
Okay, that's great. Thank you very much for inviting me to this very interesting set of presentations. I really enjoyed the previous two.
Oh, Taj, it might be the wrong screen for the PowerPoint that the presentation. I think if you switch over the screens, you probably have two screens on. So if you just reboot it, it looks good. We can see it, and we're looking forward to it. And we can see, as I just mentioned, the weather looks terrific in the UK at the moment. So it's very overcast and rainy here in Moscow.
Is that
better? I think we have it. I'll just check with our technical guys here if that is the screen we need. I believe it is, but I'm not technically minded. Guys, are we okay with the screen? Yep. Here. There we go. Okay, fire away, Taj. We're ready.
Okay. Yeah, I want to, I guess, give a slightly different perspective on energy use. We've heard some very interesting presentations at a materials level and at a sort of economics level. My presentation, I guess, is a little bit more practical, so I apologize if some of it's particularly related to the UK, but I'm going to be looking very much at the sort of why we're actually using energy, the socio-technical aspect of it, and in particular the transition that the UK is going through at the moment in terms of the transition to meet net zero carbon emissions by 2050. And I'm going to be discussing predominantly residential energy use, the energy that we all use in our homes, and briefly describe a new research instrument we've built to study this using smart meters. In some ways, it's our Hubble telescope for understanding energy demand in the built environment. So just to set some of the context for this, I mean, you know, there is plenty of evidence now that theoretically renewables, particularly solar and wind, can meet future energy demands and even a growing energy demand, and that this can be done relatively cost effectively within the existing resources we have. And I've referenced one paper here by a colleague, Professor Robert Lowe, that works with us, that has studied that and looked at the uptake. And I mean, if we're looking at targets for 2050, that's 28 years away. And so to a certain extent, we really are pretty limited to the available technologies that we have at the moment to tackle that short-term problem to 2050. Obviously, beyond that, a whole range of different materials, different processes will potentially come on stream. But at the moment, in terms of tackling climate change in 2050, we largely have to deploy many of the existing technologies globally throughout the world. The rate of change that's already happened in the UK has surprised many of us in the UK. If you'd have said a couple of decades ago that 40% of electricity was decarbonised, then most people would have struggled to see how that could happen. And at times we already have 80% of electricity generated from decarbonised sources in the UK. That only tends to be for very short periods. You just heard about how windy it was here over the last 2 or 3 days. It's been very windy, and therefore we've had some maximum generation from wind power. But in the UK, net zero by 2050 can be achieved by halving our energy demands and doubling the electricity supply. None of that is going to be very easy, but that is considered at the moment probably the most likely scenario for how we will achieve our targets for net zero. And the residential energy consumption, the energy we use in our homes, is quite critical in terms of the challenges to meet a net zero future in the UK. And I've shown a slightly unusual graph here, which compares the external temperature in the UK against energy consumption. And the energy consumption is quarterly. That's for the winter, spring, autumn, and summer, for the different sectors of the UK. And what you can see is that transport is a very large energy consumer in the UK, but stays relatively flat across the seasons. We actually use more energy in the summer for transport than in the winter. Industry is pretty flat. The non-domestic sector is relatively flat. But the big change occurs in the domestic sector. And in the winter period, we use almost half of the energy in buildings. And that's because of the dominant effect of wanting to heat our buildings and potentially in the future, increasingly air condition some of them as well. But at the moment, we're very much a heating dominated regime. And the size of our future decarbonized energy system will be driven largely by the demand in the winter period that we have. That will determine the size of the infrastructure that we need to build and the amount of interseasonal energy storage that we will need to have as well. And that's in some ways the most expensive energy storage, is if you only use it in effect once a year. In order to decarbonize all of this energy system, we're going to invest literally billions of pounds to switch to electric systems and to reduce our energy demand. And I just want to just give you one example, and it's a very crude sort of thought experiment. Let's assume we move away from where we are at the moment. And this is the same graph that you saw earlier on, in effect, a simplified with transport, industry, non-domestic and domestic. And on the y-axis, on this axis, I've plotted it in gigawatts to show you the instantaneous power that would be needed at a particular external temperature. And just to show you the challenge of electrifying our existing system, at the moment, our average electricity generation in the UK is 39 gigawatts. When we've had some of our most challenging time periods when it's coldest outside, the electricity system has coped with 50 gigawatts. So you could see that there's no way our existing electricity system could simply be converted at the moment. Domestic energy use is very much gas oriented. And if we were to power that with wind turbines, we would have to increase the number of wind turbines by a factor of roughly almost 30 times what we currently do. However, if we just do some very simple things, electrify all our vehicles, electric vehicles are far more efficient, so the transport energy consumption drops. We introduce heat pumps instead of gas boilers, and we insulate our stock. Then suddenly we drop down to about 14 times the wind turbines that we might need during the winter period. And that's roughly trebling the installation rate. So here we're now starting to talk about something that is practical. We're now installing a lot of electric vehicles. We replace roughly 1.7 million gas boilers a year. If we replace those with heat pumps, it would be possible to achieve this. And I've not made any great assumptions about how much insulation we would need to put in our buildings. So this gives you some idea of how we're looking at the transition to occur, but there will be a lot of unintended consequences, and to marshal that transition over the next 28 years is going to be really, really challenging. And so one of the instruments that the UK government has supported here is a smart energy research lab. This is being facilitated by the fact that the UK has now 19 million smart meters in 11 million homes, and we're installing about 16,000 of these every day. So we have a much greater capability to actually understand what is happening in our energy consumption in this very important sector. And what this instrument is to provide researchers with access to this data. And energy consumption data on its own is of relatively little practical use unless you could link it to other data sources. And so what we have done is we have created an observatory, a data set of 13,000 homes who are representative of the UK population of buildings and people in those buildings. And we're accessing every half hour their gas data and their electricity data. We're also linking that to the weather, and the weather drives our energy consumption, as you saw from the previous diagrams in the domestic sector. Half of our homes also have an energy performance certificate. A surveyor has been round those homes to rate its various appliances and technologies that are installed in those buildings. And then we also ask the occupants questions about how they use their building, the age of the building, and other pieces of information that can put the energy consumption into context. And as well as the observatory, which is a group of people that we're just observing in the population, we have 7,000 homes where they form part of laboratories. These are homes where interventions happen. Those interventions may be changes in behavior that people are encouraged to do, or they may be new technologies or new policies that the government is thinking of applying to try and change the energy demand in the building sector. The advantages of this approach is that we get high resolution data. Historically, we've only had annual energy consumption data. It's longitudinal. The occupants have agreed to allow us to carry on monitoring. We've been monitoring since 2018. It's representative of the great British population of buildings and people. We can release the data quite quickly. It's relatively low cost to collect because we now have the smart meters in place. And we're able to look at both gas and electricity. Many studies have previously looked at electricity only. We can use the observatory as a counterfactual to the laboratories where people are taking interventions and see how the interventions are impacting that people have introduced compared to the natural interventions that will happen. And we've had many of those recently, and I'll talk a little bit about that in a minute. We have historic data now, going back a bit of time, and it's linked to this contextual data. And something that's very key is actually also that it's safe and accessible. And in the UK, we have a lot of regulations to control the access to smart meter data, and to do that in a secure and ethical way it does involve quite a lot of effort. This sort of instrument is now up and running. We have a lot of research projects which are live. I won't go through all of these. We have government-funded projects that use this to test out various policies, and a whole range of international projects that we're now engaged with as well. And I'll just give you some examples now of the type of research areas that we're applying this. We can look at the results of natural experiments, and COVID and the current change in electricity prices is something that we're looking at the moment. We can use it to evaluate policies. We can use it to ground models that can predict the future energy consumption, either on a daily basis or on a seasonal basis. We can develop a whole range of analytics techniques with these that can help us to plan the future energy system, and can be used in a whole range of different business applications as well. And we can test the validity of other data sets that have been collected and used for other purposes nationally. And perhaps lastly, but almost most importantly, we can actually look at the progress to net zero. Like I say, we're going to go through this massive period of change over the next 28 years. Some of it will be planned, but some of it will be unplanned. And undoubtedly, there will be a lot of unintended consequences, which we need to rapidly understand. So just to give you a few examples, and I'll rattle through these very quickly because I'm acutely aware that we're short of time. Perhaps the biggest natural experiment that we've all been subjected to is COVID. This is a massive behavioral change. Perhaps the biggest behavioral change that we've gone through since perhaps the Second World War. And the question is, well, how has energy consumption changed during that period? But perhaps most importantly, how will any sustained changes continue beyond the current COVID outbreak? We've suddenly changed our working patterns. Many people, like myself at the moment, are working from home. Will that sustain in the longer term? Potentially it will do. And can we learn any lessons from the transition we've gone through at the moment? So here you can just see, just for electricity, this doesn't include gas, how the pre-lockdown and post-lockdown electricity consumption has changed at different times of the day. We've suddenly started to have lunch in the UK, which we haven't really used very much energy for lunch, but suddenly because we're all at home, we're starting to do that. And we started to learn some quite interesting things. One of the interesting things is that space heating dominates our energy consumption. And yet actually that didn't change very much, despite the fact that lots more people are working from home, home occupancy is much higher. Whereas perhaps we would have theoretically expected home working to massively increase our domestic energy consumption. Also, there is evidence that some of the big changes that would impact some of the sort of sophisticated analytic techniques that we're looking to use to help us transition towards the net zero is not really being impacted by these quite large behavior changes. And that's actually quite useful from a research point of view. We've developed new empirically grounded models that can predict energy consumption on a daily basis in UK homes. And we're able to look at the parameters which are most impact the energy consumption. So increased daily energy consumption is significantly associated with all of these factors: houses that are older, houses that are more detached, air conditioning, houses with more adults, houses that have higher set temperatures for their heating systems, and those people who don't try to save energy. So people who are motivated to save energy do actually succeed in doing that. We've also been able to identify that the questionnaire that we developed to assess the energy, to provide contextual data, and which is completed by the occupants. This questionnaire takes 20 minutes to complete. But the usefulness of that in terms of helping predict a building's energy consumption is as great as providing a surveyor, a qualified surveyor of the energy systems in the building to go around. And that's obviously much more expensive to do. And then lastly, we're developing a whole range of techniques to help businesses plan their future energy systems. So one of the big transitions we're talking about in the UK is installing heat pumps in our buildings and replacing gas boilers. Heat pumps only work efficiently at the moment if buildings are reasonably energy efficient and they're actually used in a particular way. Can we identify those particular properties using smart meter data? And can we measure the energy efficiency of the building just from the smart meter data? And it looks as if we're able to do that. And the likely case is that in the future you will buy a new house, which should be an energy efficient house. At the moment, many of our new houses are not as energy efficient as we would like them to be. And the potential is to for your smart meter to tell you whether you've been sold a bad house that hasn't got all the insulation in, isn't performing like it should be, and therefore you need to get the builder and the engineer back into the house to make sure it actually complies with the regulatory levels of energy consumption. And sorry, I'll just go back again to this. And then also, one of the reasons why energy efficiency isn't often valued as much as energy generation is that we don't really have meters that can easily measure that and take into account occupancy factors and variations in weather in terms of the impact that that has. But with the smart meters and some quite sophisticated analytics, it's now possible to start to do that. I'll skip this graph and just finish on this graph, which is from our smart meter data. This is currently how the energy consumption changes with external temperature in the 13,000 homes that we're monitoring. And you get this sort of gradient. As it gets colder, we're using about 5 kilowatts in our homes. And this is where our sort of scenarios that the government is planning to achieve by 2050. And so one of the things we will hopefully be observing is this change to this much lower energy consumption. So just to summarize, I believe it's theoretically feasible to meet net zero goals globally and in the UK. However, it will be very challenging given the timescales that we've now got left to do it. How domestic energy use in the UK changes will impact the size, type of solar, wind, energy generation that we have and the storage for the future energy system. Analysing smart meter data and other data from other Internet of Things, and it's great to see the previous presentation show that some of those Internet devices will be supplied with energy which is relatively easy to maintain. This can provide and help us monitor the unintended consequences and plan for the transition, and also develop new business opportunities. The Smart Energy Research Lab is only one of the many research projects that we have at the UCL Energy Institute. And just to sort of conclude, I just briefly wanted to measure another project that we have where we're creating a digital twin of every building in the UK. And we're well on the way of doing that. We've done it for London now. We're rolling it out to the rest of the UK. This is a three-dimensional model of every single building, what goes on in that building, and its energy consumption. So on that note, I'd like to finish, and thank you very much.
Professor Oresky, that's terrific. Very, very interesting, especially with the whole energy system. I know back home in Ireland, we always look to see just how effective we are. And of course, it guides people on what houses they want to buy, because of course, if it is green, then at least they're not going to pay so much on their electricity and energy needs. You've answered one of our questions already from Ivan Petrov, who is a Vice Dean at the Financial University, about how to be more energy effective. So you've answered that already. And one question that is here, just very, very quick answer for you if you can, from Alek Koltsov here in Russia. And he just said, what kind of perspective can you see for international cooperation on that? Because the very last one there you put up was, like analysing different buildings. How can that be rolled out in conjunction or in cooperation internationally and not just in the UK?
Yes, so I mean we're doing quite a lot of international collaboration. I mean, I guess the way to say it is really, I mean, we share a common, challenge in terms of transitioning our energy systems, and each country will transition it slightly differently. Even if we have the common goal of net zero, there are many different ways of actually achieving net zero. And those which will be most attractive will depend on each country. I mean, we're in one of the windiest countries in the world, so wind power is likely to dominate our supply. It'll be solar in other countries, for example. And so we have a common challenge. We need appropriate data. And so sharing our understandings of how better to collect, analyze this sort of data. And in terms of, for example, the digital twin, we're currently working in both Africa and India, looking at applying this approach of building digital twins to different countries to help plan their transitions as well. And we're also looking and have projects of how smart meter data can be used in South Africa as well. And so I think the actual research has to be done locally, but I think there's a lot of potential to share experience, techniques for doing this in the most appropriate way.
That is terrific. So on that note, Professor Taj Oreshkin, thank you so much for your time today, and have a great rest of your Tuesday.
Thank you.
Okay, folks, we're moving on now. We have one final presenter before we have our panel discussion. And we're staying, so 3 in a row. So we're staying in the UK, and we're going to speak with a PhD research scientist, a member of the research staff in the Electrical Power Research Group of the School of Engineering at Newcastle University. His topic is Customer-Led Distribution System, Modelling Future Electricity Network Operation Scenarios. Can't believe I said it all in one go. Timur Saifuddinov, if I said that correct, you're very, very welcome, and hello. We're looking forward to your presentation.
Yeah, well, hello everyone. It's a very nice day and it's very good opportunity to present to you my, our work at the Newcastle University. I hope you can see my screen well. Can you?
It's perfect, yeah, we can see it.
Okay. Okay. Well, again, good day, everyone. My name is Timur Seyfudinov, and I'm a researcher in the School of Engineering at Newcastle University. And today I would like to present to you our research work my colleagues and I did for the customer-led distribution system project, or my English native English colleagues say CLADS, the weird way to say this abbreviation, but well, this is the like native English speaking people says. This project is led by the Northern Power Grid company, which is the local electricity distribution network operator. And in our work, we developed a modeling framework and modeled future electricity network operation scenarios. So this is the outline of my today's presentation. First, we will look at the role of electricity networks in GB at present and what is expected when the energy sector is decarbonized in 2050. Then I will present a distribution system operator concept, which is aimed to facilitate a cost-effective transition to an emission-free energy system. Then I will present our multi-agent and multi-market modeling approach. Then we will look at the modeling setup, where we considering multiple stakeholders, their individual objectives, interactions with markets and services in a particular distribution network. Then we will look at some of the results of our modeling and wrap up with the main learnings. But before we proceed with the presentation, with the rest of the presentation, I would like to draw your attention to this graph, which is the UK's progress towards decarbonization. And as you can see from this graph, the UK is already reducing emissions almost at the highest pace. And this is mainly achieved from decarbonization of electricity supply or energy supply, switching from coal generation to renewables. However, in the near future, the different processes, we'll see the different processes occurring around us, and this is related to electrification of heating, transport, and industries, which is driven by the government decarbonization plans, which will require significant interventions to the way how distribution networks are operated. For instance, if we look at the energy flow charts here, which compares 2020, year 2020 and the expected scenario, net zero scenario in 2050, we will see how the role of electricity networks will change. So comparing the amounts of energy transferred by the electricity network in these years, we can see that the role of electricity system in the whole energy sector will increase from 20 to 80% in relative numbers, while in absolute numbers, this will result into 2.5 times increase from the moment what we observe at the moment. And so in order to facilitate cost-effective transition to the net zero energy sector, a DSO concept has been proposed, where DSO stands for the distribution system operator. So what is DSO? DSO is basically considered as an independent entity that securely operates and develops an active distribution system that comprises networks, demand, generation, and other flexible distribution energy resources. So the DSO roles include first, facilitate an economically feasible transition to a net zero energy system. Second, manage conflicts and synergies between local and whole system objectives. The third one is to deliver smart control of its networks and facilitate various forms of flexibility, including those that originate from distributed energy resources and demand. Fourth role is to enable non-network solutions to defer or even avoid network reinforcement, which can be done through ancillary services or local balancing. So by local balancing, I mean here trading energy locally, not at the national level, but at the local levels within a distribution network. And finally, the goal or the role of DSO is to support customer-centric approach in networks development. Our research, so this is the picture of our of the concept that we apply. So basically, our research is modeling interactions between stakeholders in distribution networks through markets and services. For instance, there is a DSO that may require some flexibility from DERs, industrial and commercial customers, and aggregations of domestic customers to procure distribution system service, for example, investment deferral service to avoid or postpone network interventions in order to while at the same time ensuring reliable power supply to the customers. Then there is ESO, which stands for the electricity system operator, that can procure whole system services such as frequency response or capacity reserve, so it can procure these services from the distribution network. Also, we are considering the possibility for local energy trading by customers, distributed energy resources and suppliers, as well as some other non-system operator services that can guarantee that can originate from, for example, from suppliers or other stakeholders. So the particular decision making or in this environment, or I would say ecosystem, is the amounts and prices for demands and offers for these markets. So basically, our stakeholders interact with each other through the markets. This is our assumption. And the particular amounts and prices for demands, they are, in our modeling, they are derived based on the economic models of the stakeholders, which are informed with specific data illustrated by colored arrows here. For instance, DSO demand for the service will be based on the available network flexibility, the demand in this network, and it will be also decided in coordination with other markets and services. On the other side, ESO demand for its service will be driven by external opportunities, as ESO can contract flexibility or contract capacities for its services from different locations. Then there are customers and suppliers decisions, which are informed by the price signals, which include electricity tariff and distribution use of system charges, which is basically the margin that goes to distribution network operator to cover the operational costs of the network. Now, let's look at the particular configuration of the environment that we have modeled and what we expect to have in the future electricity distribution networks. So specifically, we have modeled 5 local markets and services, including local energy market, where energy is traded, supplier service that is looking for demand reduction. Then there is a DSO service aimed at investment deferral by reducing net demand through demand reduction or calling additional generation to turn up in order to decrease net demand or net loading in the distribution system and postpone or avoid building new assets, new lines, or new substations. Also, there are two ESO services, namely capacity reserve and frequency reserve, which are similar to those procured by ESO at the moment. So this is the list of markets and services that we model within a distribution network. And the services, they are offered by the assets, by the physical assets, which have been mathematically modeled to derive their marginal cost, which is then used with with bidding strategies. So we have a taste of a game theory in our modeling here as well. And these assets, these assets that we have modeled, they include distributed energy resources, which such as photovoltaic generation, wind turbines, fuel cells and electrolyzers, some other non-renewable generation, and electricity storage. From the domestic sides, we have modeled heat pumps and electric vehicles, mostly smart charging and vehicle-to-grid technologies. And also there is an industrial and commercial demand-side response. And on the other side of this graph, there are stakeholders that place bids to the markets and services where particular amounts and prices of these bids, they are again derived from the economic models of the stakeholders that follow specific objectives. And these are individual selfish objectives of these customers, stakeholders. So this is the particular distribution network that we have modeled. This is the real extra high voltage distribution network. It is of mesh topology, and it actually accounts for 25 primary substations and one grid supply point at the bottom here, where the network is connected to the transmission system, or in our model, it is a slack bus. So peak demands, numbers of flexible domestic assets, capacities for distributed energy resources, and industrial and commercial demand-side response. All of this data were taken from the forecasts which are published online. Actually, all of the distribution network operators, they publish this data online, and it's called distribution future energy scenarios. And the particular studies that we performed for this network, they include sensitivity analysis for this wide area DSO zone. And particularly in this slide, I will be showing you studies on the values of each of these markets and services that we are considering, as well as the values of distributed energy resources locations. However, we did much more studies with this and other networks within the project. So these are specific results that we obtained from modeling the future distribution network operation scenario that correspond to the following setup, which actually require quite specific inputs for the number and location of assets, distribution, use of system charges and electricity tariffs, number of customers participating at the local energy market, and other detailed information. I would like to mention that, well, that we actually not aware of any of those details that can be expected in 2050, and especially in this network that we are modeling. So So we basically treat the obtained results more like qualitatively rather than quantitatively. Now let's look at this bar chart first, which actually illustrates lots of things. Particularly this, the black dotted curve illustrates the extent to which peak demand at each primary substation exceeds the limited capacity of this substation, to indicate whether it is required for DSO to procure this peak shaving service or not, and by what amount. So this is input data. And here are substations that are ordered in the descending order with the amount of demand that needs to be curtailed through flexibility. And the colored bars here, they indicate the amounts of capacity traded and contributed to peak demand reduction by a particular service or market. For example, we can see that the local energy market, which is the pink bar or pink bars here, they contribute significant amounts to peak demand reduction. And the supplier service, which is a yellow bar, they contribute a little. And the rest is covered by DSO, which is the blue bars, and this is done to ensure that the peak demands, they do not exceed capacity limits. So you can see this kind of a synergy between the operation of local energy markets, supplier services, and DSO objectives. So DSO doesn't have to procure the whole capacity, it just procures whatever is left after the operation of local energy market and supplier service. And also there are ESO contracted capacities illustrated with light and dark gray colors, but they do not reduce peak demand, so we do not calculate them towards the reduction of peak demand, but just illustrate on this graph. So one of the things to note here on this graph is that actually ESO procures its service from those primaries or from those substations where DSO doesn't do it. So even though that electricity system operator can offer a much higher price for its own services compared to DSO, and this actually was one of the worries of our industrial partner in this project. Would it be possible for us to compete with electricity system operator as a DSO? And actually, these results show that even though that ESO can offer much higher prices for its own services, it is economically feasible for ESO to avoid competition with DSO and procure their services from non-congested networks where DSO doesn't need to contract any capacity. And then there is another chart here which illustrates costs and benefits from procuring flexibility services within the considered network. And the whole budget here, which is the height of the bar, it corresponds to the alternative solution of network reinforcement. For example, building parallel transformers to those that are saturated with the demand. And from this figure, we can conclude that for the specific input values that we have considered, the DSO flexibility service can be procured at 1/3 of the cost of conventional network reinforcement, while the rest, 2/3, is the DSO benefit. So it makes perfect sense for DSO to consider this ancillary services in its business model. Then there is a last chart which illustrates the extra high voltage network peak utilization, and particularly the extent to which power flows in the EHV network reach capacity limits of the corresponding power lines, where 100% is the capacity limit of a line. Then the span of this interval here represents the minimum and maximum relative power flows. And the box here is an interquartile range of power flows. So from this figure, we can conclude that the considered EHV network has a significant margin of network capacity, as its peak utilization does not exceed 80% for the electricity demand expected in 2050. So these are kind of things we can retrieve from our modeling of multi-agent and multi-market system. And as I've already mentioned, we are not aware of the specific inputs that would accurately represent future networks. And since we can only guess on these values, on the particular values, it doesn't make sense to analyze the specific numbers here. And instead, what we do, we perform a series of sensitivity studies to investigate various features of future networks. For example, in this study, we have analyzed the value of the...
Timur, we'll need to wrap up on that if you can come to a quick conclusion. We're just a little bit over.
Yeah, if you could give me like 1 minute so I can wrap up.
Of course.
Yes, so basically with this modeling framework that we have developed, it's valuable to make sensitivity studies, like, for example, the one that presented here, where we compared values that originate from each individual service. For example, we did that by modeling the scenarios in which we have eliminated one service at a time. And by looking at these results, you can see that the most value here is hidden behind the local energy market, which is basically local trading of electricity or local balancing of energy. So this is this kind of indicator for DSO or for distribution network operator, where they should focus their business plans. So yeah, I guess I can stop here, and thank you very much for your attention.
Thank you, Timur. It's fascinating and very, very interesting as well, especially from the kind of purely analytical side. Got one kind of question it's the relatively same question from two people, one from Deloitte, from Elvina Fauzatinova, and you're a student from Kazakhstan, Togjan Nusulbek, and they both are asking, because you're based in the UK, what's the difference in terms of, the analysis you did? What would you see the difference in the energy system with Russia and the UK?
Well, I think one of the main difference here is that, well, Russia is big, and the Russian electricity system is very huge, and it mostly relies on gas-powered stations, while now we see this very, very high transition in the UK towards low carbon generation, and actually they have switched to from coal generation to renewables mostly. And another thing, so this is the supply part, but another thing to keep in mind is the demand side. For example, I don't quite see it feasible for Russia to accept all these technologies all developments in mobility, in the electric vehicles, especially battery-powered electric vehicles. So this is actually one of the big niche for the UK to decarbonize, while in Russia, well, these low temperatures, they are actually not complementary to battery technologies at the moment. And so I guess we will see these kind of differences which are linked with the environment.
Okay, that's a great. The difference in the carbonization is extremely important. So, Timur Saifuddinov, thank you very, very much, and have a great rest of your Tuesday.
Thank you very much, and see you all. Bye.
Okay, and now, folks, we move on to the midsection, I guess you could say, of our forum today. Of course, it's the panel discussion, and I'd like to have three experts in the field of green energy. And I'll say from my, it's slightly different line up here as in terms of the position here on the stage. However, you know, I'm a sports coach, so I'm supposed to know how that works. So the Doctor of Economics, Professor, First Deputy Dean of the Faculty of Economics and Business. He's Professor of the Department of Industry Markets at the Financial University and a member of the Public Council under the Ministry of the Russian Federation for the Development of the Far East and the Arctic. A very warm welcome, Ivan Petrov. Next to him in the middle, of course, you already know him. He opened up our forum here today. So I won't go through his full title because he had a brilliant opening performance for today. Yuri Plakitkin, you're welcome back. And finally, I say last but not least, at the very end of the panel, and wearing a blue shirt just like me as well. So I think we're kind of like measuring it quite well. He is the Doctor of Technical Sciences. He's a corresponding member of the Russian Engineering Academy and head of global energy problems at MPE, the university here in Russia. A very warm welcome, Vladimir Klimenko. I'm going to start off actually, Vladimir, because I've introduced you last. And the question I have is very, very simple. We're talking about decarbonization. But is green energy the solution to decarbonization? Or should we be looking, as we discussed at the very start of the forum, a dual path? Microphone.
Могу я попросить мою презентацию, пожалуйста?
May I ask to bring my presentation on the screen, please?
Ну, пока открывается моя презентация,
While the presentation is coming
я
up,
хотел бы высказать несколько, может быть,
I wanted to start with a bit of provocation.
не являются выдуманными, а являются реальными. Пожалуйста, пролистайте.
Can we go down a little bit down the slides? One more. This one. Okay, let's begin here. So basically, we are talking about green energy and the energy transition. We talk about decarbonization. And then you may be asking, why? Why do we need it? An hour ago, Professor Plakitkin explained that possibly this energy transition is something inevitable. This is how human civilization develops, and energy transition is only natural to humankind. So the question that I've just asked makes no sense. If it's part of our nature, if it's the way of our life. But Professor Plakitkin's statement is somewhat philosophical in the context of what we have seen the last decade, and especially in the last years. The answer to the question why decarbonization and why energy transition is climate change. I believe that climate change is real. It's not fiction. Climate change must be addressed, and what do people think today about how they can combat climate change? Well, the general idea is that we need to cut down the emissions, especially CO2, greenhouse gases. The concentration of CO2 in the atmosphere is the reason of the additional greenhouse effect, which leads to high temperatures on the planet. At the moment, the temperatures are up 1 degree versus the averages of the second part of the 19th century. It's 1 degree exactly, and on this slide you can see the program of measures to reduce greenhouse emissions until the year 2030. I don't know if you can see all the details, but at least you see that there are many different colors on this chart, and it shows you that not green energy nor decarbonization on their own will not be able to solve the problem. Just with green energy, for instance, will not be able to cut the emission of greenhouse gases in half in the next decade. We need to take massive action to cover all areas of life of a modern society. There is no silver bullet. There is not one solution, a universal solution that will enable us to solve this problem. Out of the multiple sectors on the chart, the biggest share belongs to renewable power. This is energy, basically. Renewable power sources must or can solve the problem of greenhouse gases by 1/4, but that's just a quarter of the solution. What are the other 3/4? Like I said, they are all possible areas of human activity, and probably the most important one in terms of preserving the climate are things that are pretty far from the topics that we discuss here today, like forests. I will come back to forests later, but for now, let's see whether humankind is actually capable of solving the decarbonization problem. Here you can see the energy intensity variation. The energy intensity is the number of CO2 tons emitted into the atmosphere when 1 ton of coal equivalent is used in all kinds of fuel, in any kind of fuel. Decarbonization means less carbon intensity, and the lower lines on this graph is what is supposed to be happening under the Paris Accord. And the Paris Accord doesn't lead to the resolution of the climate issue, and the Paris Accord alone does not allow us to sustain the temperature growth. From this graph, you can see that until now we were not succeeding very much in addressing the issue. The Paris Agreement, its requirements are quite moderate, and the equivalent or coefficient should be reduced by about 0.8% a year. But you can see the black lines there. We so far managed to achieve only 0.5% reduction in this coefficient. We also see that after the record decline in the first year of the pandemic in 2020, in 2021 we saw a kickoff, and the carbon intensity increased again. Energy transition and green energy, the problems that we discuss here today are very difficult issues, probably the greatest challenges that the humanity ever faced in the times of the civilization.
Okay, we have to move on to our next speaker, so thank you for that. Ivan, I'm just going to ask you, the main barriers, because you're working in the financial university, the main barriers for a full rollout of green technology, financially, is it useful? Can it be a good business?
Of course, as representative of the financial university, I should be speaking about energy not only as a resource but also as a market. And as many before me have already pointed out, the market is determined by supply and demand. As someone representing a financial university, of course, I'm here to say, or I'm supposed to say, that it's a beautiful business, and we understand that any business will not be able to survive without resources. Every business needs resources. Energy is a resource. In geopolitics, we also see that energy can be used as a resource of geopolitics. But that's one hat that I wear. The other hat that I wear is a researcher in nature management economy, and the younger generation, the students, those who are looking into the future, they are very much interested in this, interested in this side of the coin. So once again, here we also see supply and demand, and if all political efforts, administrative efforts, are aimed at generation of energy, for some reason people tend to forget about demand. Again, I'm all in favor of demand. Demand is a good thing. When there is a new car, or if there is a new smartphone introduced to the market, and those cars, those smartphones, they become old already in a couple of years. I remember in the past when a car would last you for half a century. So basically, demand also matters, and there is demand in natural resources management, energy management. Half of people living on the earth do not have access to cheap energy. We can continue reducing our emissions and at the same time fail to provide the other half with affordable and accessible energy. One of the first questions today was about renewable sources of energy. So being economists, we should always do the math. We need to compute financial flows along the whole product life cycle, production, operation, utilization. You know, there are technologies today to capture CO2. When you capture it in the atmosphere and it's present there throughout the cycle, and it's captured from the atmosphere and it's injected into wells where probably there are aquifers. And looking at this globally, water resources for many territories is a more acute, is a more relevant problem than the problem of CO2. CO2 is invisible, we don't see it. We are not thinking about the future. Well, I mean, we understand, we have a general notion of that, of changes in temperature and everything else, but there are more immediate problems that affect people living in certain territories. To take viable decisions or economically feasible decisions on green energy, I need to understand it. Right now, I don't understand the pricing. And ESG is one new approach, actually, to all kinds of economic and financial decisions. Why not? We can also use this one. Well, the ecosystem, in the last presentation, we saw an ecosystem. I believe also in ecosystems when financial, environmental, and societal interests are all taken care of. As a consumer, I need cheap and available energy. I need to be able to access it at any time. And we have already noted the value of the energy. I mean, in the past, of course, our light bulb went off. Fine, we can always light a candle, but there are some processes that can't be interrupted in terms of energy, that where life depends on energy, like in operating theater, for instance. So we need to take into account financial, environmental, and societal interests.
No, very, very good. Again, the ecosystem no, that makes sense to have them all working together. Yuri, a question for you on this is coming from Galina Deryugina. She's a student. She's a professor in MEI, and what she wants to know is, because you were looking forward, what are perspective technologies? How can we integrate that into what we have right now, so to phase out well? We start off with decarbonisation. We looked at the finance involved and how to make money from it. But how can we phase one out into the other?
This is an interesting question. Before I answer it, the question that Alan asked about barriers, it also has a bearing on this question. So I want to start first by discussing barriers and then move on to your question. So Alan asked an important and relevant question: what are the barriers to alternative or green energy? In fact, as all things new, when there is a new product, usually new products tend to be very expensive at the beginning, and at the beginning every technology is expensive. But after some time, things that used to be expensive become cheaper and then cheap. Because of scientific progress, technological progress, that always finds more cost-efficient ways to produce certain products. Wind, solar energy, we remember how expensive they were in the beginning. We see that solar or wind energy generation performance is improving year on year. As the more the technology spreads, the cheaper and the more efficient it becomes. The second barrier that is usually cited in the context of new sources of energy is their reliability. Many think that they are not reliable. Winter, summer, strong wind, low wind. So many believe that this is a limiting factor. Well, actually, no. We can work around it. First, we can create storage and accumulation systems for energy. And there is hydrogen. Hydrogen that can be used as this major capacitor, as an accumulator, whenever there is a shortage of energy generated by other sources. And one other aspect. What is the biggest barrier today to implementation of new energy? I think that the biggest barrier is the multinational energy corporations that own this industry. And I understand the shareholders very well, but of course the shareholders would like their business to have a long and a profitable life. So of course they do everything in terms of ordering research that would confirm their point of view, their position, and in terms of information spreading and awareness raising. They are hedging their business against competition with the new sources. And I think that we are at this point precisely when the governments need to push for the new agenda, so that the bigger corporations would see that there are more business opportunities in the new line of work. And now to your question about phasing out old technologies and integrating old infrastructure with the new infrastructure, phasing out old infrastructure. As the first speaker at this conference today, I opened the discussion. Basically, my answer to this question is energy has its way. It follows a certain path from the low calorific equivalence to the high calorific equivalence. So I will answer this question with another question. In 30 years' time, for instance, in that future, will we still want to integrate with the low calorific equivalent infrastructure? Do we still need to integrate back into the current thermal energy infrastructure? Modern day energy is 80% thermal power plants that consume conventional energy sources and that leave a big carbon footprint. And at the same time, we have a lot of wires around, local, interregional, regional, national. I'm not an electrician myself, but I know that these networks have colossal losses, up to 50%. So do we need to integrate back with this old-fashioned infrastructure? Well, the answer is no. I think that for the past 150 years, in thermal energy, we've been trying to improve the Carnot cycle, the performance of the power plants. Maybe we should stop doing it. We can't spend another 200 years trying to increase the productivity. Probably we should be looking for new avenues. The energy of the future probably is not large-scale systems. The energy of the future are mobile cells. We see that energy is becoming miniaturized. So a small generation, high density generation. So I'm thinking this is what many people do today, and the solar generation that we get from the sun should be integrated not into this old system, and we already have this integrator. Hydrogen is called hydrogen. It would be wonderful if we built an integration system around hydrogen. So you generate solar power, and yes, it's not very stable, but at the point of instability, we have a wonderful opportunity. We've got storage facilities for gas already, and we can fill them with hydrogen. And whenever there is shortage, we can always retrieve hydrogen. So hydrogen will not be the main source of energy. It will be a source that will gradually level out, balance out the shortages in other energy sources. So integration is possible, but on a different platform. Solar energy is getting out into the open space. Like I said, we know already about the projects on low orbits, and then there will be geostationary orbits. We need to think about new kind of integration. Low orbit and energy can be integrated with ground-based energy. And the emphasis should be on power cells of different nature, like hydrogen. Oh, I'm sorry, I got carried away. I'm sorry. So that's how I think about integration.
No, it makes perfect sense. Again, and the new technology as well. Vladimir, just looking at Russia as a whole, is Russia taking advantage of the natural way of generating energy, for example, with wind energy or solar energy? Is Russia making the most of it, and can it make the most of it?
Очень, я бы сказал, непростой вопрос.
Now, this is a difficult question you're asking.
К сожалению, нет.
The short answer to your question is no.
В прошлом году,
Russia isn't doing enough. Last year, well, not last year, it was in 2020. According to global statistics, Russia produced 3.5 million kilowatts of power out of renewable sources. China produced 863 billion megawatt of power out of renewable power out of renewable sources. Russia currently is in the 52nd place between Costa Rica and Honduras with its 3.5 billion kilowatt hours produced out of renewable sources. There is a strategy in Russia that was adopted 2 years ago, and it preserves Russia's Russia's arrears in renewable energy sources by 2035. So what it aims at is to achieve current levels of Romania or Poland in the year 2035 in terms of renewable energy generation. So once again, Russia is a laggard, and Russia still focuses on gas and other fossil fuels, and unfortunately not renewable sources of energy. A couple of words about renewable sources, if I may, because it's not that often that we discuss this context. Humankind not only developed along with various energy sources, but humankind has always been fighting for energy sources. There were oil wars, there were gas wars, and there are the so-called critical materials, cobalt, lithium, rare earth metals. The geography of localization of these materials is very different to the more conventional natural resources. 60% of cobalt reserves are located in one country, which is the Democratic Republic of Congo. And the same applies to lithium and to rare earth metals, even if in a smaller degree. Unfortunately, Russia, apart from cobalt, doesn't have any other critical metals. So the country needs to undertake significant effort in order to overcome the future disadvantage. So there is the problem of depletion of these natural resources and the fight for the natural resources. Recently, we did an extensive research and we published the findings in a leading international paper, Review of Sustainable Energy. Again, we know about the current plans for the development of world energy, and we wanted to match these plans against available resources. The findings are not very promising, unless
развиты вновь
there is development
технологии
of
повторного использования
recycling or reuse of
то уже
cobalt and especially lithium, then by the middle of this century, the humankind will be left without these critical resources. The recoverable reserves of cobalt is 7 million tons. Every year, 120,000 tons are mined. So you divide one number by the other, and you will see that we are left with only a couple of decades of the production of this resource. Since this conference is hosted by the Moscow Institute of Mining of Alloys and Steel, it's very opportune that we talk about the criticality of resources. In the next decade, one of the focuses should be on recycling, the reuse of lithium and cobalt and other rare earth metals.
Okay, it's a bit worrying, but okay, thank you. Ivan, coming back to you on just on this, continue kind of the moving from resources and the cost of resources, because we went from kind of what renewable sources of energy are good. We're moving around on this. A question to come in about the tax, because I've seen, for example, in Russia, in Ulyanovsk, they have wind turbines, windmills. So, what tax breaks can be used in Russia, or what can help to develop sources of green energy?
В настоящее время действуют механизмы.
Well, at the moment, there are mechanisms. Tender can be announced, and solar energy or wind energy projects can win in the tenders and receive special, well, they're not subsidies. In fact, the investor is guaranteed to pay back the investment through a higher tariff. A higher tariff, of course, will have to be covered by the consumer of the energy, which is not a good thing. But there are other tools as well that can support renewable sources of energy, the carbon footprint and control for the carbon footprint, and certain AC innovations, EU innovations for the companies that export their products into the European Union. You'd probably know about the boundary tax. In Russia, there is a system of green certificates. When I buy energy out of green sources, and I can promote my products as greener and environmentally safer if they are produced with clean sources of energy. We also know that what's related to decarbonization and sustainable development requires reforming taxation, especially of production industries, mining industries. You know, there is a tax on extraction of natural resources. Some companies pay a higher rate, others get a lower rate, but basically there is a need for the environmentally unstable industries to have a new taxation system, which can also be based on the so-called carbon footprint. I know that these matters have been discussed, they have been studied. It's clear that any change in taxation should not happen overnight, so to say. It should not be sudden, because many investments have already been made under the current terms and conditions of taxation. But in new projects, especially if it's a project in the Arctic, I believe a government decision is required to implement a new taxation system.
You've actually led me to my next question. This question, this Yuri, is for you. It's, in terms of the Arctic, lots of questions about the, saving the Arctic and the melting of ice caps and so on. What energy can be used in the Arctic? Just an example, like in fragile areas, whether it be rainforest or whether it be the Arctic or just in Russia and the Arctic, that can actually save the environment?
Вообще вопрос этот достаточно
This is a very big question.
можно поставить так, расширить даже.
It can be made even bigger. What are the which energy sources produce the least harm, be it the Arctic or tropical forests? The Arctic is vulnerable. It's more vulnerable compared to other regions. So for the Arctic, that matter is extremely relevant. We know about the damage coming from energy sources. Basically, all energy sources are damaging. They are all harmful, one way or another. I will not talk about coal, gas, and oil. We know about that. Colleagues talked about CO2 emissions and the carbon footprint. So definitely this is not the road for the Arctic. It's not a good option. On the other hand, in the press and in the scientific community, you sometimes find another position. The alternative sources, aren't they detrimental? Yes, they too can be detrimental, like the windmills, the wind turbines. They are creating vibration, and vibration is damaging to the earth, and gophers and other small animals that live in the area can be affected, can die. It's very difficult also to recycle the blades on the windmills. It's not clear what to do with the blades. And as to solar cells, solar panels, they're next to impossible in terms of recycling. So human activity is damaging. The question is how much, how big is the damage? So we need to understand how much damage we create for the environment if we use conventional or alternative sources. We can compare coal power plants. A coal power plant consumes several, trains of coal, and they are emitting into the atmosphere and everything else. But if it's not coal, if it's a source with a high energy density, well, many people don't like nuclear or thermonuclear power, but you don't need many trains. You need only grams, kilograms maybe, of the actual fuel to power such a station. So the higher the density, the less a primary fuel you need. The more productive the energy, the higher is energy efficiency. The less is general consumption of energy. And finally, if we talk about the remote future, when solar generation is, transferred away from the Earth into the space, then the impact will be even smaller. So to answer your question, in the Arctic, the least damage to this fragile environment can be achieved by using high energy sources and alternative sources of fuel. Some good decisions have already been taken in the country. I will not go through all of the list, like floating stations, nuclear stations. it can be one option that will sustain the livelihoods in the Arctic, and it will be good, environmentally safe solution. Less coal, oil, and gas, and more high
Okay.
density
that
energy.
It makes sense. It sort of is almost contradictory, but it does make sense. So I do understand it. We're going to have to wrap up now in a moment. So we'll just go 30 seconds quick around. Start off with Vladimir. Vladimir, in 30 seconds. Okay, and I'm timing it. What one thing would you want to change in Russia to really make people wake up that they need to sort of, to be more, aware of conserving energy? So same question to each person. So 30 seconds starting for you, Vladimir.
Ну, знаете, если коротко и за 30 секунд,
Well, if you're only giving us 30 seconds, in Russia there are enough laws and regulations that should be taking us in the right direction. The problem is to be consistent and persevering.
поставленные перед нами трудные задачи будут решены в ограниченном.
There are no challenges. The challenge will be able to achieve our
Very good
goals.
answer. Okay, we'll go straight to you, Yuri.
My answer, a very quick one, is
надо задуматься, первое, задуматься и перенести себя, провести мысленный эксперимент.
you have to set a thought experiment. You have to think back 30-35 years, right? And you look around which technologies we had 30 or 35 years ago. And then you can extrapolate this experience onto the next 30-35 years. And then you will see that actually scientific progress and new technologies
Это громадный шаг в будущее, а этот громадный шаг должен обеспечить...
is propelling us into the future. And this
Very
propulsion
clear.
needs energy sources, new energy sources, clean ones.
Может только в одном, что в первую очередь надо изменить финансово-экономический
We need to change the financial and economic model
деятельности, в том
of distributing the output, the results of operation in the energy and fuel complex. The whole model, economic model, must be changed. And also, the behavior of individuals must change. Those who consume resources, let's save energy.
So save on our energy. Thank you. To Vladimir Klimenko, to Yuri Plegitnik, and to Ivan Petrov, thank you very much for your time today. I will just wait with me for a moment, and we're going to go straight away back to the UK, to Maria Sharmina. She is an associate professor in energy and sustainability at the Tyndall Centre for Climate Change Research at the no? Oh, Andrew, very, very good. Okay, I see it just here. Okay, so we just mix up. So, yeah, so we're actually staying in the UK. I'm going to Andrew Lovett. He's Professor and Director of Learning and Technology, Teaching School of Environmental Sciences at the University of East Anglia. That's out in Norwich. So, Andrew, you are very welcome to the forum today and looking forward to your presentation on integrating natural capital into energy transition assessments.
Good afternoon, everyone. I hope you can hear me and see me okay.
Yep. Yep.
So I'm just going to talk very briefly about some of the research I've been involved in, working with a number of people on how you might try and incorporate issues to do with natural capital and sustainability into the assessment of energy transitions. To provide little context, this is one of the key sorts of challenges the UK faces, how we're going to decarbonise our energy system. Several other speakers in the event today have talked about these issues, so I won't dwell on this, but you can see from the graph there how the makeup of electricity generation in the UK has changed in just over the last 20 years, and the decline of use of fuels like coal and increasing use of renewables. But this transition is going to have a lot of challenges. We're moving away from the subterranean energy sources, coal, oil and gas. We're making much greater use of renewables, wind power, solar power, bioenergy. As you can see on the little chart there, they have much lower power densities. You need much more land footprint basically to generate the same amount of power. and we're moving to a system which is much more decentralized, which has been mentioned also by previous speakers, and much more potential interaction with other land users. And that's an issue for the UK and many other countries, because we're also looking at how we can try and improve our environment, how we can better incorporate our stocks of natural assets, the natural capital, and the ecosystem services, the benefits that human society receives, and incorporates those into decision making. And the UK government has got formal commitments to try and do both of these things, both decarbonise and also incorporate natural capital and environmental considerations into decision making. And this is a bit of a problem, because at the moment these energy and environmental policies, certainly within the UK, are not at all well integrated. If you take something like the government's 25-year environment plan, which was published in 2018, it has very little about energy in it. There you can see on the screen a word cloud of the executive summary. The word energy is sort of hidden in a tiny corner. So we need a way of better connecting these areas of research and policy. And the project that I've been involved in leading the last 6 years is funded by the UK Research Councils, the Natural Environment Research Council. It's a project called Advent. It's all about addressing valuation of energy and nature together. It's part of the UK Energy Research Centre. You can see the web address at the bottom of the screen. It involves 7 partner institutions. It's involved about 35 different researchers at different times and 7 PhD students. And it's all about trying to develop conceptual frameworks and modelling tools that will allow us to bring these 2 areas together, to integrate the analysis of prospective UK energy pathways with considerations relating to the value of natural capital. And this is an output from a recent research paper published in Environmental Science and Policy. It's actually a contribution from the 7 PhD students that were funded by the Advent programme, and it's an attempt to try and conceptualise what would need to be done to take energy system model outputs, which tend to be very strong on the temporal dimension and weaker on the geographical and spatial dimension, and start to try and put them in a form where you could assess environmental impacts and you could develop mechanisms and tools that would allow you to think about energy transitions that would meet decarbonisation objectives, but would think about issues to do with sustainability in terms of other impacts on the land and marine environment, and would be publicly acceptable and would be socially just. So we need to think about this conceptually, and we need to think about it in terms of modelling tools. And this is something that we've done within the project. It's a piece of work that's been led by researchers at the University of Exeter. And we have developed a model which divides the UK into 1 kilometre squares, and it looks at land use information, and it looks at the potential uses of that land for wind farms, for solar parks and bioenergy, and it determines the targets that might be needed based on information from national energy system models. And then it starts to determine where you might begin to locate those to optimize different sorts of criteria. And very importantly, we're trying to do that in 2 different ways. We're trying to do it looking at the market, the financial costs. What will it cost to construct these facilities? What will it cost to connect them to the electricity transmission and distribution network? What will be the opportunity cost of land? What will be the transport cost for things like bioenergy feedstock? So that's a sort of optimization problem. But then what we've also done is think about it in terms of the non-market externality costs. And one of the distinctive things of the research is the range of things we've tried to consider. So we've looked at visual impact, we've looked at carbon sequestration, water quality, implications of land use change for flooding risk, implications of land use change for pollination services, crop yields and biodiversity, and what it would mean for recreation. And we can start to run these models and start to assess different pathways using these combinations of evaluation criteria. And here's just one example of the type of result. So this is taken using the outputs from one of UKIRK's UK Times model low carbon energy pathways through to 2050. What would the distribution of the necessary solar, wind and bioenergy output look like in the UK if you were just to take market values, and you can see where the facilities are located? What would start to happen if you built the non-market benefits and costs into that decision making as well? And you can see it changes the pattern, it changes the pattern of land use, it changes where you would locate things. We have a framework here that we've implemented in the UK. Clearly you could take these ideas and apply them in many other countries as well. So this kind of spatial explicit modeling is very important. It starts to give you an idea of where to locate infrastructure to minimize costs, the impacts that are associated with not considering ecosystem service costs and benefits, the scales of land use change that might be involved, and where different sorts of land use conflicts and network constraints may occur. So that example is looking at where you might locate things. Another way of thinking about it is to consider it in terms of regional planning. So this is output from an EU Interreg project, RENES, that I'm involved in, where we're working in the east of England, where my university is located. And we've divided the region up into small administrative areas. There's about 600 of them on the map. They've been categorized in that rather colorful map that you can see in terms of two different variables: their potential for renewables generation using onshore wind, solar farms and bioenergy, and the different sorts of natural assets they have in terms of high quality agricultural land, woodland, protected areas for nature and recreation areas. And what you've got there is kind of where are the different combinations occurring. And the important point in this region is a lot of the area is in that orange category, yellow, the kind of category 9 that you can see on the map. Basically, these are the areas which are high potential for both of these sorts of axes. So you've really got to start to consider the trade-offs between these. You've got to look at ways in which these land uses might be made compatible if it's possible. But equally, you can start to identify areas where there might be opportunities for increased renewable energy generation. So category 7 has high renewables potential, but low values of other natural assets, and there's clumps of those areas, and they might be particularly good in terms of developing renewables in the region. So this wider environmental project, RENES, is working with partners across 5 countries in Europe, and what it's all about is trying to integrate these considerations regarding renewable energy generation and other land uses in different sorts of land use planning and policy instrument frameworks. But I think this is really important if we're going to achieve decarbonisation in a way that's really going to be as environmentally beneficial as possible. Thank you very much.
Andrew, that was terrific presentation, and great to see the regionalisation as well of how you can actually target areas where it's more possible and more efficient as well. Thank you very much for your time today, and have a great Tuesday.
Thank you.
Thank you. Okay, that was Andrew Lovett, of course, from the University of East Anglia. We're staying in the UK and going just up the road, kind of to the north northwest, yeah, I got it right, to the northwest of the University of Manchester, and to Maria Sharmina. She's an associate professor in energy and sustainability at the Tyndall Centre for Climate Change Research at the University of Manchester, and also a senior academic advisor on the UK government's Foresight project, Net Zero Society, Scenarios and Pathways. Maria, you're very welcome, and we're looking forward to your presentation.
Thanks very much for the introduction, and hello everyone. So I'm based in Manchester normally at the Tyndall Centre for Climate Change Research, but I'm currently on a secondment with the Net Zero Society Foresight project, and that's what I'm going to talk about today. So just to give you an idea of what the project is about and who I'm working with. So this is the Government Office for Science Foresight Projects, and what they do is try and identify where emerging new science can inform policy in a useful way. And these projects have to have a significant future element, and that's why they're called Foresight projects. So it's got to be either quite high uncertainty, or it's got to be a long-term issue, for example, climate change. And so some of the examples of past projects include future of manufacturing, of cities, of the sea. And this particular project is on net zero emissions, which is the UK government's target by 2050. And so I'm advising on both technological and societal behavioral challenges, which is, you know, we will need both if we want to achieve that target. So technological changes are not enough because they would take a bit of time to put in place, whether it's renewable energy or any other kit or infrastructures. And so this part of the project I'm going to talk about is examining trend data on different societal behaviors that drive energy demand and emissions. And this work is, you know, fairly broad, so there's less depth to it, but it's quite broad because it looks at different sectors of the economy. And so these are the sectors we are looking at in particular, so materials and products, which is industry, mobility, or you can call it transport, residential and non-residential buildings, and finally there's nutrition and land use, or agriculture. And so under these 5 sectors, we have identified several trends that are quite important in terms of driving emissions. And there are about 30 trends, I'd say, in total. And these are you know, they have different data sets associated with them. And so the point of this work is that we want to keep an eye on those trends. If they drive emissions, we want to see how they have changed so far and what is it that's causing those changes. And so that's why we've been looking at the data. And so just a few examples. So for the materials and products sector, the industry sector, household consumption is very important. So the stuff that we use, buy and discard. For mobility, it's obviously traffic flows by different types of transport. For buildings, it's floor area. So how many buildings do we have and how many are we building? And a few other things like heat pumps, for example. And here I have to point out that, you know, I was talking about behavioral changes as important, but, you know, heat pumps are technologies. So in this case, it's about a mix of behavioral changes and adopting those technologies that are already available, but there are barriers that are non-technological. So there might be cost, financial barriers, or there might be barriers of perceptions. And if we move on to what sort of data sets we've used here, so this is just examples from this presentation, but in total there are around 35-40 data sets for each of these trends. And I have to say that there are some trends that we're not actually tracking yet, so there is no data to observe them. And one example is retrofits in the non-residential buildings sector. So we don't know how many buildings that are non-domestic that have been retrofitted. And I'm talking about the UK, obviously. So just some of the results. So some of the trends that we have looked at have been immediately impacted by COVID, by the pandemic, for example, travel. So on the left-hand side, you can see a graph of travel demand, where obviously it drops in 2020 for most types of transport, apart from bicycle trips. But then for other sectors, like construction of offices and homes, they will be affected in the longer term. For example, the number of dwellings completed in 2020, 2021 actually did drop because of the pandemic by about 10%. But in the longer term, the patterns of leisure and work, like working from home, for example, might affect how many buildings we would construct in the city centres. So longer term impacts. In terms of the sectors of materials and products, or industry and agriculture, it's consumption that matters most for emissions. And if we look at the graph, figure 23, so the graph on the right-hand side, so this is actually calorie consumption. So energy consumption is what it's called in the data set, but it's calorie consumption. Of course, it matters how much we eat, because it determines how much food we grow and waste. And interestingly, reported calorie consumption has been falling over the years. So we've been eating less and less in the UK, but there is a big caveat to that. It turns out that we are underreporting our calorie consumption by probably about 30 to 50%. So we are actually eating a lot more than we're reporting we are eating, which is a problem when you want to observe those trends, and might need to adjust the statistics and how they are collected. Okay, so on the building sector, of course, solar PV and heat pumps are important. So that's the data sets we're tracking. And on mobility, it is traffic volume or traffic flows. And so this graph on the right-hand side is actually billion vehicle kilometers, as opposed to the earlier graph I showed you, which was the number of trips. So this is the length of trips. You can see that in the UK, cars are really dominating all the other modes of transport. Probably true about a lot of other nations, including Russia. Okay, so what underlies those changes, those trends? So in the orange box, the one on the left-hand side, there's some of the traditional drivers, like economic growth, cost, and the performance of certain technologies that we might want to adopt, and government support. And on the right-hand side, the grey text box, we got less anticipated drivers, like supply chain disruptions and shortage of critical raw materials. So the panel before this session mentioned cobalt. That's one of the important ones. Lithium is another one. And of course, there are parts that we need for electric vehicles, for example, chips. And the more positive driver, the last one, showrooms and eco-home events. So apparently, there's some evidence that it's helped with the spread of electric vehicles and home retrofits. So this is something that might help with heat pumps as well, because some of these technologies cannot actually be tried out within one couple of days and then you move on to what you had before. Heat pumps, if you install it, pretty much you're stuck with it, and it can be quite disruptive as well. And so trying that out in showrooms, touching them, relating to them, something that might help with those trends. Okay, so that's all from me today. Thanks very much for your attention. And if you have any questions, please get in touch.
Maria, that was absolutely fascinating. Just one little small question for you, just as our next guest walks across. On that, with trends, what do you think could be a trend? We were speaking earlier on about future. What could be a trend in, say, 15 years, would you reckon?
A trend within, do you mean in a particular sector?
Yeah, I would say, well, in just I would almost say like consumer sector rather than industrial or business.
Yeah, I think one of the trends we were looking at is, I'm talking about the UK, reshoring the manufacturing. So you might know that in the UK, a lot of production moved to countries where it's cheaper, where labor is cheaper, and that's driven a lot of the territorial emissions down. And moving emissions, essentially offshoring emissions to countries like China. And so now we're seeing a trend that countries are thinking about reshoring, so returning the manufacturing capacity back to the UK, which would affect emissions, territorial emissions from the UK. So I think that's one of the trends we need to keep watching.
Okay, really, thank you very much for a wonderful presentation and a great answer as well, and have a great rest of your day.
Thanks very much.
Okay, and now we're moving on, and we're going to come back here to Moscow for the moment, and we'll speak with the senior researcher in thin film photovoltaics here at the National University of Science and Technology, Ms. Cease. Delighted to welcome onto the stage to present his topic, Emerging Printable Photovoltaics for Alternative Energy Sources and Novel Applications. Daniil Saranin, the stage is yours.
Many thanks for the invitation for today's speech. Today I will represent the interesting message from the researcher in photovoltaics. So let's go. I hope it will be interesting. So today we will speak about emerging printable photovoltaics and alternative energy sources and novel applications. So do we have enough solar power on our planet, and is it competitive to the other energy sources? Of course, if you will compare the scale of all power density from solar, wind, hydropower on the slide, it will be a huge difference. So we have the interesting calculation that if we will convert 100% of 1 hour solar power, it will be equal to the year of power consumption for the humanity. So it means that we have enough power to convert into useful electricity. Another point to discuss, do we have enough sun everywhere on our planet? Of course, we have some uniformities, but there is a parameter, insolation, which represents the power density falling to the unit of the square. So scientists have calculations that only blue and green zones are not relevant for the use of solar power for the mass electricity charging. So you can see that even in Russia we have enough solar to convert it and use. So what are current energy systems? Current developed solar systems are based on silicon technology, and this is a standard chip-like technology based on wafers, and humanity spent more than 50 years to develop the technological processes, and now mostly they are placed in Asia. So they can be attractive more or less. So this is a real solar farm in China, and it more and more comes to our life. So, but what we should take into account, of course, money. Everyone is paying for the modern conveniences, and only after of the beginning for the 21st century, we have the real decrease in the price per watt for the generation of electricity from the solar light. So why it happened? It happened because all the major facilities were transferred to Asia. But is it competitive to the modern fuel technology? So now nuclear power give us approximately 2 US cents per watt, and the price per watt for the solar energy is 1 order higher. So this is a big difference, and maybe when we will start to pay, we will think, maybe we will burn more trees and or use more atom energy. Of course, my own feeling that this should be a political decision to move to the green energy sources, and of course it should be continued to be co-funded with the government, because it should be a political decision, not just economical. So let's go next. What is a current solar technology? As I told before, this is a silicon wafers humans spent more than 50 years to develop very advanced structures, actually heterostructures based on silicon, crystalline silicon, amorphous silicon, and this is more than 90% of the market. So currently we have no real competitors for the existing technology. There are some myths about new breakthroughs in solar technologies. So one of these is a company SolarCity and Tesla, so solar cells from Elon Musk. So actually this is a technology of Panasonic that is packed in a very beautiful way, though this is a solar cells which are resistant to the mechanical stress. The standard price for the 1 square meter of solar panel is $40-50 US. But if you want to buy the beautiful solar cell from Tesla, you will pay more than $200 US. And this works for California, probably, but not for the rest of the world. This is my feeling. What is a dream? So you could see the slide with a chart representing 3 generations of photovoltaics. The first generation is showing us the balance between its efficiency and cost for the fabrication of 1 square meter. And with existing wafer technology, we couldn't put it below the 20 US cents per watt, even in warm countries near the equator. So the only one hope is for 3rd generation photovoltaics that should be extremely cheap and extremely effective. It should be as cheap as and something common for us. So maybe like a printing of the newspapers. So it should be recyclable materials and it should be high throughput fabrication. So do we have the candidate for this? Yes, we have the new competitor, Noble Semiconductor halide perovskite. This is a hybrid molecule based on organics, tiny content of lead and iodine. Exactly the presence of lead and iodine tends to the formation of unique semiconductor properties which are competitive to silicon as well as for gallium arsenide. But what attracts a lot of scientists and industries, it could be done in solution processing. So we are moving from the conventional electronics with the clean rooms, with a heavy industry, high vacuum, high temperatures, doping as well, for something obvious for consumers. Everyone has an inkjet printer in its office, in its house, of course, and the approach is the same. So we should develop a special ink. So if we will add to perovskite oxygen, it will be classical perovskites, but if we will add iodine, it will be halide perovskite, which absorbs the light more stronger than silicon. So you could see on this slide that it's even more effective for the absorption of the light than gallium arsenide, which is mostly used for space. And this is a thin film technology, and we could manufacture semi-transport solar cells, and it could be used as energy effective windows. And before perovskite, it was just a proposal with organic semiconductors. But with perovskite, it starts to compete with silicon. But do we have another concept for the light conversion, excluding the solar roofs or solar farms? And the answer is yes, it should be smart conversion. So if we are speaking about direct solar light, we could have the concentrators and the solar roofs. But if we are speaking about low and indoor light, we could discuss the charging of portable devices, IoT, and variety of sensors which are start to enter our common life. So how it's look like? As I told before, it could be done as a semi-transparent window which is converting direct sunlight, indirect sunlight, and office light. It could be device integrated, and it could be sticked as a very small photocell without any problems with the curvature of the device. So here in Mises, we developed a special process for the printing of thin film perovskite solar cells in ambient atmosphere. So we have no clean room. We are using the slot die printing technique, and before this technology was used for the photography. So now we could use it for fabrication of solar cells. So let's say it's a reinvention of old technology for modern applications. You could see that we need just to choose the appropriate ink, then anneal it at small temperature 100 Celsius, and then we could see the conversion of the photoactive layers goes in very fast way. So the cycle for the fabrication of solar module will be as long as approximately 5 hours. So that's why a lot of hopes for this technology are for perovskites. Only one vacuum process is realized for the fabrication of these solar cells. We should deposit just the metal film, and this could be replaced by the printing of carbon. So there is a field to develop and to make progress in. Okay, let's move next. So how we applied it for the smart conversion of energy. We showed that it's possible to charge IoT sensors. So we used Bluetooth Low Energy, which now is a key device for the communication of the smart devices in your home. So it's like a gate for collection of all messages. So that's why if you wanted to design a smart house, before you need to think how to put the tons of wires inside of your flat or house. But with use of indoor light conversion, you shouldn't think about it. You could put the devices as a magnets on your fridge. You should think only about the entrance of light. What could we charge with a low light? Of course, we couldn't heat the water and boil it with the indoor illumination. Of course, no. So mostly it's RFID, remote control, and wireless sensors, Bluetooth, and several protocols for the Wi-Fi. Do we have lots of such devices? Yes. Before, in 80s and 90s, we were able to charge only calculators and watches with the indoor illumination. Remember, yes, there was a gray-like solar cells on the calculators. It was a technology of amorphous silicon. With use of perovskite, we could increase the power, the generated power, in more than 5 times under indoor illumination. So that's why we could charge more and more devices with a compact size of a solar cells. Before, with silicon, with well-established technology, it was impossible. But with perovskite, it's possible to create a new niche for effective energy generation. So here, one more time, we could point out the protocols of telecommunication that will be autonomously charged with indoor conditions, so RFID, passive Wi-Fi, Bluetooth Energy, and ZigBee. So a lot of things for the smart house as well as for Industry 4.0. So modern industry is impossible without autonomous communication of the devices between. So that's why even with the design of new industrial place, we should not think about the wires. We should think only about our comfort. And you need just from 1 to 10 square centimeters, so no large solar panels, to make it autonomous and wireless. So Novel Energetics should be smart energetics. It will be realized with a smart agriculture. We have a lot of places in agricultural sector without direct sunlight. So in the shadow of trees. And silicon is not working effectively in such conditions. So you use perovskite. Consumer gadgets. Of course, we couldn't stay all the day under direct sunlight. We'll have the heat shot for our head. Use perovskite. So we have the new, the novel concept for the urban modern conveniences, and of course we could effectively convert office light, LED light as well, and non-direct sunlight. Use perovskite, of course, and finally for IoT, this is only one way to convert effectively the low light intensity. So that's it for today. I'm ready for your questions. So today it was a very brief intro, so maybe I could help you with explanation of the details. Halide perovskites represent a novel material for optoelectronics application with a record solution process solar cells. So this is a quite unique combination of the high potential semiconductor properties with a cheap technology which could be realized with a common printing techniques. Many thanks for your attention.
Okay, Daniel, that's terrific and very interesting as well, especially it's happening within our walls here at the National University of Science and Technology in Macis. A question was sent in by a viewer, and it's from Anton Pankratov, and he's an assistant professor, and his, for example, he said, what is the maximum? Now we're talking here about like, you know, how to say, how to reuse light, like you said, indoors. Like the very final thing was just very interesting. And what Anton asked is, how much light can we reuse?
It's of course it's it will be simply to operate with the digits, with the numerical stuff, and at now here in place where we are now, I think it will be 400 lux, not so much. And from 1 square centimeter, we could extract more than 60 microwatts, just from 1 square centimeter. So if it will be 10 square centimeters, so multiply for 1 order, so on and so forth. So not so huge to boil the water, please, it's impossible, but enough to charge our mobile phones, our earphones, so on and so forth.
On that, just continue on, Daniel. In terms of reflect, a lot of time we know in Moscow, for example, I think it was last year before, we had about 10 days of actually sunlight. But I know myself, because I'm pale skin, it could be sunny, or sorry, not sunny, it could be clouded over, quite warm, and you still get kind of a sunburn. So does that work as well? That it doesn't have to be direct sunlight, does it?
Yes. So what is a problem with the common technologies for the silicon crystalline semiconductors? So when we have a direct sunlight and we have a standard conditions, we have 1,000 watts per square meter of falling light. Yes, it's enough. And silicon is working pretty well, so its power conversion efficiency is high as 24%. So from 1 square meter, we could effectively extract approximately 240 watts. Perovskite is working with the same level of efficiency at direct sunlight. But when we have cloudy weather, silicon is falling below 8%, while perovskite is going up to more than 30%. So this is the big difference in physics for the operation of solar cells. But of course, if we will solve all the fundamental problems of perovskite and say so, and we'll tell to humanity, no way to silicon anymore, you spend 50 years for nothing, perovskite will save the world. Of course, it will be a mistake, because silicon is working well for 20 years. Perovskite for now, just few years. So that's why we couldn't, it's not available in the market. But the smart energy consumption will be realized with a balanced niche application of different solar cells. Solar roofs and direct sun for silicon, indoor conditions, and scattered light for perovskite.
Perfect. Daniel, on that, thank you very, very much. Daniel Sarahin, of course, here working with us in the National University of Science and Technology in Macis. Thank you very much for your presentation and your answers today as well.
Thank you too.
Okay.
Hopefully to see you offline.
For sure. Okay, so we're going to move on to our next speaker. And unless I'm mistaken, even though I've given it a slightly different signal, I believe it is Professor Furong Li. He's the chair in electrical power systems and director of the Center for Sustainable Power Distribution at the Department of Electronic and Electrical Engineering at the University of Bath. Of course, oh, it's Philip. Thank you very much. Okay, it's slightly changed here. So I'm delighted, well, staying in the UK in any case, and to the Imperial College in London, where it still looks a bit sunny, Philip. So at least you're enjoying better weather than here in Moscow right now. He is, of course, a research associate at the Department of Physics at the Grantham Institute for Climate Change and the Environment. Philip, really looking forward to your presentation today.
Great, thanks very much. Let me just share my screen. Okay, hopefully you can see my presentation. I can't see you.
Yep,
so
it's coming through loud and clear.
Perfect, thanks very much. Thanks for extending the invitation, and thank you for the introduction. My name is Philip Sandwell from Imperial College London, and the work I'm presenting is on behalf of myself and a few other colleagues, all about our energy system modeling work. So we're taking a bit of a turn into a different area. So we've gone from applications of PV indoors and now we'll be going very much outdoors and focusing on developing countries. So to start off, it's worth acknowledging that around the world, there's around 750 million people that currently have no access to electricity whatsoever. So that's around 10% of the world's population have no access to electricity. Many more of those have access to poor quality electricity, so maybe it's unreliable, maybe it's dangerous, and often it's very unsustainable. The majority of these people are located in the developing world, and as the graph on the screen now shows, the blue areas are where the need is greatest, and typically this is in sub-Saharan Africa. Looking back to the previous speaker's presentation as well, this is also a region of the world that is blessed with the most sunlight. So there's a huge opportunity for solar photovoltaics to provide electricity access and getting people the first step towards the kind of electricity services for modern life that we're enjoying right now by virtue of you being able to hear me across the continent. It's also worth acknowledging that when we work in this kind of development world, we're really trying to achieve the Sustainable Development Goals. So SDG 7 is sustainable energy, but it also links with all of the other 16 goals for a total of 17. So energy can be a real enabler in terms of providing clean water and food, reducing poverty, supplying healthcare. Imagine if there was a hospital without access to electricity. It really is an enabler across the board. But when it comes to supplying electricity, this isn't just a binary thing. It's not a case of you have no access to electricity and then you have the kind of access that we have right here. It's actually more of a scale. So there's a system that was developed by the World Bank, kind of splitting levels up into levels going from level 5, which is what we have right now, all the way down to level 0, which is no access to electricity, and then different steps in between. So you can see there's kind of a graduation from the most basic energy services, which would be level 1, 2, going into the kind of more modern conveniences that we enjoy. But what this does is it gives us real like interesting conundrum. So when it comes to providing electricity access, how far do we go? How far is it affordable to provide the best quality of electricity, but admittedly for some of the poorest people in the world, how do you make that balance? The way we do it is through energy systems modeling. So it lets us explore lots of different options for system design, different combinations of technologies that might be most appropriate. So I said earlier that solar is particularly appropriate, but maybe it's also wind power or different kinds of battery technologies or perovskites rather than silicon. Maybe there's lots of different future scenarios we'd like to see. What if we want to support the development of a community that requires greater energy use for businesses or for agricultural processing or all these kind of modern conveniences we would hope to aspire to over the next years. It also lets us look really at the technological performance of these systems, so we can look really into detail about how they perform hour to hour or even higher resolution than that, but also look years into the future. So we say right now this community is not too developed, but if we are able to supply them with electricity, how will that demand grow over time as the community develops, more businesses spring up, as they have greater economic integration with the rest of the world. And it really lets us kind of have a little checklist of all the different things we want to achieve, typically with standalone systems. So most of the systems that are being deployed in the developing world in remote and rural areas, they're called mini-grids. So they are small, independently operating electricity systems, independent of the national grid network. They're entirely self-reliant, and they're meeting the needs of that community that is typically very far away or in a very rural region of a country. The way we do it at Imperial is through this energy system model called Clover. I won't go into too much detail. I don't want this to become an advert, but I would like to say it is all open source. It's all available. And if anyone in the audience would like to learn more, the website's available there. It's all free to use. And we've applied to lots of interesting case studies. The summary is that it has lots of different components, which look at lots of different applications of energy resources, how the energy is used, the different energy demands of a community, how they might grow over time, and ultimately optimizing systems to suggest which is best for a given application, how you can tweak its performance to get the most out of it, and ultimately inform the companies that are building these systems, the NGOs that work in these countries, the government agencies that develop the strategies for rural electrification, really how we can take that research and give it to them to be most useful. The way to simplify this is that really we look at energy supply, we look at energy demand, we look at the balance of those two factors, we assess the performance, say which one we think is best, and then the most important thing is taking action to do something about what you find out. And the important thing of these kind of smaller scale systems is there's lots of variability. So we heard from the previous speakers that understanding or building a model for something is a relatively simple process. You can have a computer model that calculates whatever you want. The hard thing is when you start integrating real systems and the variability that comes with those real systems. Like, people are not computers, things vary, people have different needs and desires, and it's quite hard to quantify what someone wants in terms of like an accurate prediction of the energy demand that will meet that need they want. And when it comes to these smaller systems, all of these variabilities get magnified, because if you have a system that is operating on its own, it needs to be entirely self-reliant. If you have big fluctuations in solar resource, for example, so if you have lots of sunny days or lots of not very sunny days, that system's on its own. It needs to be able to have the resilience in that system to still provide electricity to those communities. Within smaller communities, you can still have lots of variation in demand. So going into a community that's never had access to electricity before, how do you quantify what people will, what appliances people will buy? What do you provide for them? How much will they use different appliances? These are all questions that are very hard to answer before a system gets built, but that's why people like me have a job. You also have the kind of seasonal variations. So a lot of these regions are equatorial, but they also have things like rainy seasons, which can have lots of demand for higher power applications like heating and cooling. There can still be a lot of seasonal variation. And ultimately, the thing that we've been trying to stress is the growth of energy demand over time. So in lots of places, the energy demand is incredibly modest. We're talking people have access to a few lights, maybe a phone charger. Sometimes that's all, but that's not what we want for the next 10 years. We want these communities to develop and to grow, and for the energy demand to basically be more realistic to what we have in the countries that we are all located in. So how is that going to grow over time? What does that mean for a system that is installed today? How is it going to perform in 10 years' time? And then there's lots of interesting questions about how you operate a system. If you have something that exists, do you choose to use as much solar energy as you can? If you have a diesel generator or a grid connection, how do you prioritize those to meet your goals? And when we talk about goals, these could be things like, how much does the system cost, bearing in mind that we're working with some of the poorest communities in the world? How do you minimize CO2, given that we want to have sustainable electricity? What kind of system design is best? And best means very different things to very different people. What if demand grows over time? What if some new technology becomes available? What if different government policies change? These are all the kind of questions that we aim to answer through energy systems modeling, so we can answer those questions before these systems get built. We can look into different future scenarios to make sure that we have the best understanding of how these systems will perform under lots of different configurations, so that when someone goes and builds one of these systems, they will be best informed about how it's going to operate. It's possible to take out a few broad conclusions. So, for example, in this graph, it's showing more reliable systems from the left to the right. And typically, if you have a more reliable system, it's more expensive. The idea of having a reliable system is a bit silly to us because the electricity network in our countries is typically very reliable. But that also comes with a cost. So if you're building a very reliable system, it becomes very expensive in these kinds of areas. So where's the trade-off? So if people are happy with 18 hours of electricity per day, if that's a lot cheaper, maybe that's a more appropriate system, even though 6 hours a day, they get nothing. What if it comes into offsetting CO2 emissions? So typically, the more reliable systems have lower CO2 emissions, which can seem counterintuitive, maybe. But it's through things like offsetting the alternatives people have. Like if you don't have an electric light, maybe you're using a candle or a kerosene light, which have much higher costs and emissions. So if we provide an electric alternative, that's far superior. Or what if we're an NGO or a business that's building a system, but we only have a certain amount of budget? So in this last graph, if we have $50,000 to build a system, how reliable can we make it? So given that we are in a very resource-constrained environment, what's the best we can do with the resources we have available? How can we make it as cheap as possible or as reliable as possible, or reduce the amount of CO2 the most? The example I like to draw upon is a really nice case study that we've worked on. So it's a system in a place called Mahama Refugee Camp. So it's a refugee camp in Rwanda, which is a very small country in Central Africa. And within it, there's a refugee camp that serves the needs of I think it's about 50,000 people currently living there, mostly displaced from Burundi, which is just to the south. And within this camp, there is a health center. It was previously supplied by a diesel generator because, of course, if you are a health center, having access to reliable electricity is your #1 priority. We worked with a company which installed some solar generation, some solar panels on its roof, some storage, some battery storage within it to basically make the system more renewable. Not 100%, but steps towards it. And then they approached us and they said, how can we change the operation of the system? So we have the solar, we have the batteries, we have the diesel. They were running a strategy which was quite conservative, and they were like, we think we can get more out of this system if we change the operational strategy. How can we reduce the costs, which is basically the #1 priority of UNHCR, the refugee agency? How can we reduce those costs? Secondarily, how do we reduce those emissions? And ultimately, how do we connect some of these businesses to the system? So nearby, there was a marketplace, or there still is a marketplace, where refugee businesses had no access to electricity. It's a goal of many of these humanitarian agencies to extend the benefits of this system to displaced people themselves. So how can we use the benefits of this system and share it with the community as well, but acknowledging what kind of impact does that have on the system? So we were lucky enough to be able to monitor the data. So on the screen now is how we monitored data over the course of 1 year in 2020. So we were taking data from that system that was being monitored, and then we used some data from another site nearby to represent the impact of those business customers. So these are small businesses like phone charging businesses. So if you're a refugee and you can't charge your phone in your house, you would go to one of these businesses to charge it for you, for example. Others are available. What happens if you add these to the system? What happens to the performance of that system? So what we were able to play with was how deep you cycle the battery. So for those who know a lot about batteries, this is a very big question. If you cycle your battery more, you get more use from it, which is great, but it also degrades the battery. So there's a trade-off there. We could also play around with when the diesel generator was started and stopped during the day. So typically in the daytime, we have solar energy. You don't need the generator. At nighttime, you might do if your batteries are depleted. So playing around with these, we could answer this question of how much should we use the battery versus the generator. I don't have time to go into the details of this graph, but basically we simulated lots of different systems, about 250 in all, of all different combinations of these parameters. And the questions we were asking is, how do we save the most fuel, but also how do we avoid the system being dangerously low in terms of the energy available? So green was where we started. We saved some costs by moving over here into this region, and we use more of the storage by moving up here, which is great. So we've managed to find this purple combination, that kind of save fuel and manage to keep the batteries safe. The yellow system here was depleting the batteries too much. It had some impacts on the system reliability. It wasn't as good. So we managed to find an alternative. We could also look at what kind of businesses we have access to. So surveying those businesses in the camp, converting that very human need for electricity services, like thinking about what these businesses really want, and then saying what kind of electricity services does that translate into in terms of the numbers behind it. And then ultimately looking at the profit and loss. So looking at if you charge different rates for businesses, you know, this is a commercial operation, it's not charity. These businesses are paying for their electricity. We could say if you charge this kinds of rates, you'll probably lose money. If you charge these kinds of rates, you'll probably make a profit, which is ultimately what the mini-grid business wanted to do. And, you know, it's entirely within their right. So in conclusion, we managed to find that, unsurprisingly, installing lots of solar and battery capacity on a system does save you a lot of money, but you can actually save even more just by running it better. So this is really important because as more of these systems come online in developing countries and also in refugee camps, we really need to be getting that extra sort of 10% that we managed to get for free, essentially, by just changing how the system's operated. If you run it under a tariff that's pretty similar to the national grid, you're probably not going to make your money back. But if you let the companies run their systems just like they do in other communities, they can actually save money and they can even reduce their costs and start making a profit on the system entirely. So we can achieve the goals of reducing fuel costs, reducing emissions, and supporting these businesses all at the same time, sustainably, both environmentally and financially. With that, I'll close. I think I'm just out of time. If you'd like to find out more, there's lots of documentation available online. It's all free and open source. And with that, I will close. Thank you.
Philip, an excellent presentation. Thank you very, very much. And again, the work being done in, it is kind of South Central Africa, terrific, and it's a great example to give as well. One very, very quick question. How easy was it to roll out in an area which, you know, will be sort of more distant from most of the production facilities?
Mm-hmm. It is challenging. Like, there's no two ways about it. You know, the logistical challenges of getting equipment to these kinds of sites is a lot harder than, you know, most developed countries. That being said, once the system is there, the benefit is so huge because it is it's the only system available. Like, it's more important. Like, you know, therein is the importance of doing it correctly and doing it right. The costs are, of course, higher. Just the shipping costs alone are, you know, increase the costs. But it's still a commercially viable opportunity. There's lots of companies that are doing this, and, you know, with customers who are very poor, and they're still making money, and it is a sustainable business, and those customers are very happy to receive the energy. So it's a bit harder, of course, but it's still worthwhile for all involved.
Isn't it great? And on that, thank you very, very much for your presentation today, and for that answer to the question as well. Very, very important as well for people who are looking to go down that route, especially for in an investment strategy type. Thank you very much, Philip Sandwell, of course, from the Imperial College of London. And we're staying over in the UK, going a little bit west of London, and finally we have our next guest on air, Professor Furong Lee, Chair in Electrical Power Systems, Director of the Centre for Sustainable Power Distribution at the Department of Electronic and Electrical Engineering at the University of Bath. And we're delighted to have you here, so the floor is all yours.
Many thanks for the warm introduction. Just allow me to share my screen.
Of course, your presentation is titled Grid Integration Challenges of Low Carbon Technologies. So I think it's something that we're moving in that direction all the time here today. So we can see your screen, so away you go.
Excellent. So just give me 1 minute. Thanks very much for UK-Russia alliance for this warm introduction. So my talk is focused on grid integration challenge, largely in the UK, because the UK is among the few countries in the world had the fastest pace of decarbonization but the UK is also the first few countries actually see the low carbon challenges. And so when we're talking about renewable, although the title is renewable energy, but that's also including kilowatts electric vehicles and heat pumps. I would like to use in this graph to illustrate the pace of decarbonization in the UK. This diagram shows the daily share of coal generation in total energy mix between 2012 and 2020. The x-axis is 365 days of the year. The y-axis is the share of coal power generation. Of course, black representing coal power generation, and the green representing renewable. So the darker the color, the higher percentage of coal generation. You can imagine that coal has been a really important energy sources in the UK since the Industrial Revolution, and continue to be so until very recently. And you can see that between 2012 and 2015, the dark color is still dominant. It's not until 2016 the color becomes lighter, and in 2017 we started to see the very first no coal day, i.e. the no coal generation over a 24-hour period, and by 2019 we extended this no coal days over 2 weeks. By 2020 it's extended to 2 months. So here you already see UK colleagues today showing energy mix, how they changes over the past 20 or 30 years. And you can see that coal power generation dropped very dramatically, almost by 40% in the past 10 years. Wind generation increased by almost 700%, and the carbon intensity reduced by almost 70%. On the other hand, as I said, that UK is a few countries among the world, such as Ireland and Denmark, also see low carbon challenges. It does see a rising system balancing costs, as shown in the graph on the right. Balancing costs were the 5% of total generation cost, wholesale generation costs in 2010. By 2020, this raised up to 20%. We also see increased price volatility and also increased supply risks. For example, 9th August in 2019 is for the first time for a very long time, UK see almost 1 million people lost to supply interruption between 15 minutes to 50. That's a clear sign of increased renewable generation, reduced system inertia, and increased transmission and distribution interactions, which is all new to the system. So in terms of grid integration challenges, I would classify into energy balancing and system balancing. So in terms of energy balancing, it's basically supply demand out of two, and this arises from increased misalignment between low carbon supply and traditional rigid power demand. Can be generation forecasting error, demand forecasting error, generation shortfalls. For example, the diagram on the top level is showing under forecasting of wind generation in a high demand period. So if it's evening peak, high demand, if you're under forecasting wind, you actually suffer. You essentially have a less generation than you need. It's quite difficult to source extra generation at peak time, therefore causing extreme high prices. In this case, it's in 2020, the balancing costs shooting up to over £2,400 per megawatt hour versus the average of 40 megawatts per megawatt hour. and also you could have negative prices, that is over forecasting demand in a low demand and high wind period. For example, that if you have a low demand, already low demand, and you plan your generation to meet even lower demand because you over forecasting your need, and that's resulting surplus of generation causing negative prices. So in short, renewable generation, especially arise from forecasting error and misalignment between generation and supply, can cause extreme high prices or negative prices. On the other hand, you also have system balancing arise from a long distance power transfer because renewables, especially in the UK, come from offshore, and they tend to locate in Scotland. Your load center in southeast, southwest, so you have long distance transfer that cause thermal problem, voltage problem, frequency problem, and the stability, and also making black start much more difficult in the absence of significant thermal generation. So a typical example is May 2020. The system had 100% renewable to meet demand. However, it's a low demand period causing voltage and stability problem. National Grid got to curtail 140 gigawatts of clean energy in order to make space for thermal plant. So essentially, we spent £19 million to reducing clean energy from 100% to 80% in order to addressing system problem. And this kind of system balancing issue becomes more and more as we increasing our renewable generation. So in 2020, the country spent 1.4 billion in system in balancing cost. Last year, as gas pricing shooting up, we would imagine this figure would also increase exponentially. So here is some research BAS is undertaking to help system operators reducing its reliance on thermal plant, but moving more towards a battery storage-based system operation. For example, in this example, it's with regard to frequency responses. You could have a faster responses from energy storage, but it's had a much higher price as shown in the bottom of the table. But if you call for conventional generation to respond to frequency responses, such as a gas power plant or a coal power plant, the price is much cheaper, but it had slower responses. So BAS research here is essentially compare the value of a fast response battery storage responses versus conventional thermal responses for a system with different inertia, i.e. different degree of penetration of renewables. So here that if you look at left-hand figure, if the system inertia is high, i.e. the renewable is relatively low, system is dominated by gas and power plant, the value of fast response and slow response are actually similar. By 2030, as we have a large, very significant part of offshore renewable energy, then the value of a fast response would be 3 times more than conventional responses. So this is only one of the many things that system operator could try to reducing its heavy reliance on conventional power plant in balancing system and balancing energy. And National Grid in the UK pledged zero carbon operation by 2020. And that zero carbon operation doesn't mean that we would reach there for every single day over the year. But we aiming is it's like no code day. We start with 1 day, but over time we can expanding this 1 day into 10 days, 2 months, over time, 2 months, 4 months, and then gradually by 2035, hopefully we can get this for the whole year. We demonstrating that storage had huge potential for system operation, for zero carbon system operation, and where those storage comes from. And what we are saying here that our cities have huge storage capability embedded in our vehicles, in our buildings. How we could organize in this mass energy storage that can support national grid or system operator to reducing its reliance on thermal generation and benefit net zero transition. Here, challenges for this transition is we have limited visibility of distribution system, particularly the last mile, which have a direct interaction with the electric vehicles and heat pumps. We also have limited understanding of energy, customer energy usage, storage capability and flexibility at significant scale. We also have a very limited incentives and certainly don't have any granularity to allow energy customers to change their energy usage behavior, particularly for vehicles and heat pump when they have a huge, much higher flexibility. Limited understanding of how to organize these highly fragmented customer resources that would benefit for the grid, but also not compromising for customers' comfort and needs. I would quickly go through one project. We went with local utilities to say how to improve the visibility of low volt network templates if we want to integrate these low carbon technologies quicker and cheaper. The easiest is you install monitoring devices in every single substation, because currently they are blind, they are not monitored. So the low volt network templates essentially try to answer 3 big questions. Do we need to monitor every single substation in the UK? Are there any common patterns? And can we use these common patterns to estimate substation load profiles without expensive and extensive monitoring devices? So against these 3 questions, WPD installed monitoring devices over 800 substations from Newport to Swansea, South Wales in the UK, and really try to find out the key patterns. The left is the monitored information over 1 year at 10 minutes interval over 800 substations. And using big data analytics, we were able to detect 10 typical patterns for this entire system. And we also extending this over for this whole UK and find out with only 800 substation installation, we can detecting this common pattern, and using common pattern we can we estimate whole UK's substation load profile and get roughly 85% accuracy. So essentially we are saying that a small data set possibly sufficient for the entire system. I think that my time is up, so I would conclude on the current operation practice, low carbon transition really placing great pressure on system balancing, leading to very high system balancing costs and much more volatile electricity prices, that including extremely high and negative prices. Value of energy storage increasing by manifold, and this energy storage not only can come from grid scale, but also virtual grid scale, i.e. come from cities. we also know smart data analytics can provide cost-effective alternatives to get significant insight into both customers and distribution network, and enable them to contribute to low carbon transition alongside with the supply system. That's all from me.
Okay, Varun, thank you so much for a brilliant presentation. One quick word, just in the very conclusion there, just a little question. We've seen now the cost of the carbon fuels rising. Do you think that, like your suggestions, your implementations, can they kind of help that a little bit, just in terms of trying to balance it out?
I think that what you really want to do is really, you can decouple the energy take from grid and the energy use at customers. Currently, whatever you use, sorry, if I can stop my.
You're fine. Your presentation is fine. You're coming through loud and clear to us. Okay.
So currently, whenever you use energy, you need to directly take energy from grid. So regardless if grid is your grid price is extremely high or low, you are a price taker. But if you have significant energy storage, then you can say, if energy price is high, I could decouple this. I can using the energy stored in my system, or I can stop using for a period of time for my electric vehicle. I don't need to charge my vehicle at this moment in time. I can wait. So I think that the flexibility can really decouple energy take from grid and energy use at end user. I think that is a very significant part. But the challenge is grid, it works with millions of households. So individuals' action is drop in the ocean. So if you are the only one person in the city reacting to the grid challenges, it wouldn't have any effect. So the bigger challenge is really how you can mobilize in the citywide resources, highly fragmented. But you can also provide a bit of a consensus. So that is where advanced mathematics, advanced data analytics, and also energy management system got come into play, and how you can organize in this organic system to meet up with these man-made largest power systems.
Okay. Professor Varun Lee from the University of Bath, thank you very much for your time today and for an excellent and very in-depth answer as well. Thank you.
Okay, thank you.
Okay, and now we say the best to last always in every forum, and I think we're definitely doing that here today, with a presentation on the National University of Science and Technology, MISIS, on the way to integrating in the global model of ESG for sustainable development. I am absolutely delighted to welcome onto the stage for his presentation the Director of the Competence Centre, Professor of the Department of Foreign Languages and Communicative Technologies here in MISIS, and of course our former Vice Rector for Academic Affairs, Dr. Timothy Edward O'Connor. You're very welcome.
Большое спасибо. Уважаемые коллеги, добрый день.
Thank you very much, dear colleagues. Good afternoon.
Обсуждение концепции применения устойчивого развития, и особенно в контексте умной энергетики, задаются
dear colleagues, in conclusion to a very interesting and in-depth discussion around the concept of sustainable development and smart energy, additional important questions should be considered. First, it is difficult to argue with the model of structuring various activities with a reference to sustainable development, and still we should ask ourselves, what tools are needed to ensure sustainable development? Especially since it's the nature of every business to increase profits from year on year, while the governments set out to grow the GDP. Secondly, there is already not only the notion but also the experience of sustainable development in relation to business. For example, all over the world there is talk about the need to ensure green financing. And what is really important is to achieve, if not in the short term, then in the medium or long term, carbon neutrality at least by 2050. But the picture is different when it comes to socialization. And in this regard, let's take a moment to consider a socialization model called ESG. It is not just about environmental sustainability. It is also about corporate and, more notably, in the context of today's discussion, social sustainability. It is often said that bold decisions lead to big changes. But in fact, the opposite seems more accurate. Big changes lead to bold decisions. And in this respect, my apologies. In this respect, and despite the fact that humanity seems always to have struggled to cope with reality, in the 1990s the term VUCA appears, describing the world around us as volatile, uncertain, complex and ambiguous. There is also a general consensus that global challenges can be addressed by means of adaptability. Well, again, who can argue with this principle? But it is a real challenge for higher education, and especially for the leading universities of the world, because one of the primary responsibilities is to be example of ethical corporate behavior in alignment with the ESG principles. As of late, the world's leading universities standing at the forefront of science and technology are indeed combating climate change and promoting green business practices, proving that businesses can be fair and promote social mobility without sacrificing their profitability. Of the three components of ESG, the letter G stands for governance, and it is the basis of all other practices. It is the driver of sustainability, especially if we add one more word to it, shared. That is shared governance. Shared governance is an attempt to find a balance between the authority of a leader's position, and the opinion of the team. However, shared governance doesn't translate into Russian very well. It is often translated as управление or management, but it's not really the same. The closer to the notion is the matrix model of university management, in which both internal and external stakeholders are involved in monitoring the decision-making process of the university's administration, which certainly requires revising the entire managerial and financial models. Moreover, let's assume that we succeed in doing so for the sake of future generations. The question then is, what professional competencies and qualities do we need to form and develop in students in order to end up with ESG specialists who clearly understand that their most important task is to serve the collective or any community that needs support. In this context, universities should strive to create a facilitating, comfortable atmosphere for the personal and professional development of all students and employees. since in modern higher education, not only students but also researchers, fellows, and professors are all learners. Discussing sustainable development today from different perspectives, one cannot help but think about what cross-cutting skills will be required of our graduates, not only, say, at the end of this current academic year, but also in 5, 10, and even 20, 30, 50 years, to finally meet the challenges of the work world while ensuring that our graduates, regardless of their specialization, have social awareness and a deep sense of not only personal but also collective responsibility. That is, how do we structure the educational process so that our graduates and the next generations would care not only about the environment but also about social justice and equal opportunity for all? Well, I don't have a definitive answer to this important question. However, historically, different times posed different challenges. And every generation had its own priorities in terms of subjects, disciplines, issues, the study of which at the time seemed most important for the sustainable development of a society as a whole. For a long time, the focus was on studying philosophy, theology, mathematics, medical and engineering sciences. More recently, it is generally believed that the system of higher education, regardless of the country, should be built along the lines of STEAM, science, technologies, engineering, arts, mathematics. Information technology and computer science, along with life sciences, have come into demand not only for job market reasons, they are also perceived as relevant in the long term. In this respect, it is possible, through appropriate discussions, to determine what basic education each university should provide to its students in accordance with its mission. But in my opinion, it is much more difficult to determine which methods and technologies we should use in the educational process so that our graduates successfully master the ESG model. Now it is often said that we need to personalize higher education. But how to do it in practice? Higher education is never cheap, even if economic development is sustainable. Well, history can help us find the answer. At the turn of the 19th and 20th century, the first engineering company was founded in Russia by a talented Russian engineer who was also an American citizen, Alexander Veniaminovich Bary. Alexander had excellent leadership skills. He took bold and sometimes unexpected decisions in business. His daughter, Evgenia Bary, writes in her diaries, "Daddy never lectured adults or children about morality. When my mother reprimanded him for this, he replied that you could only teach by example." A leading engineer and a leading educator, I think. He's a good example of an educator. In my opinion, it is the only way to nurture leadership skills and to promote the ESG model in the higher education. To go back to specific examples, and I'm sure that every university present at this forum could share its own experience, I would like to discuss a few cases from the practice of Mises. Well, first of all, we've got this wonderful, absolutely wonderful lab for personal digital fabrication. It's called Fab Lab. It makes a significant contribution to the transformation of mass production into personal production. This lab, in the summer of 2019, carried out an intensive joint student workshop with the University of Paris-Saclay on plastic recycling. It was an important event as it demonstrated how sustainability can be embedded into an ESG model. At the same time, it was also about environmental protection and teamwork, especially as it was an international team. The participants came not only from Russia, but also from France and the USA. It was a real case of people's diplomacy. Despite the incredibly difficult challenge of the pandemic, in 2020 and 2021, we were able to plan and implement a students' project in partnership with the Swiss Embassy in Russia on separate waste collection. It may seem trivial. Why even mention it at all? But the project focused on environmental protection, and it helped make Mises greener as a corporation. Moreover, the participants of this pilot project, which are students who live in one of our campuses, took a conscious action at the local level, and many of them now agree that similar efforts should be made at the macro level to enable a green society of the future. Why these examples, small scale they may be, are in fact so important? They are important because the ESG model doesn't differentiate between participants in terms of their age and status, nationality, or gender. At the same time, of course, the university's faculty and staff and students worked in the projects as coaches and coordinators. So in the words of Alexander Bary, or, if you prefer, in the words of modern pedagogical theory of adaptive learning, all participants of the projects acted coherently, consciously, and they led others by their own example. Dear colleagues, wherever we work or study, I suggest that we take them for our model. Thank you.
Timothy, thank you very much for a brilliant presentation. I'm standing because my legs are getting sore from sitting down all day. It's fascinating, and one question just I came up with during your presentation was ESG is understandable, especially outside of Russia. In Russia, not so much. It is a difficult kind of comprehension because we sort of see it has to be top down, but what you're proposing and what you suggest is kind of from like sideways or from bottom up. So what are the first steps, for example, that can be implemented to sort of ensconce or to instill ESG in Russian universities? And if you can give an example here in Mises, for example.
Thank you very much for the question, an excellent question. Well, you see, very often when we talk about modern university, we naturally say that a university should enable discoveries, should provide opportunities for discoveries, for a free discussion of all matters that concern us. And we also usually talk about inclusiveness. If a university is inclusive, then it must provide the physical infrastructure. We are standing here on the stage right now. If I were in a wheelchair, for instance, or if I were wearing crutches, how would I get to the stage? No way. I would be standing here on the stage, maybe somewhere close to the stage, but not on the stage. Again, if we want progress, we have to set goals and objectives, and we should be moving towards them step by step. We can't make a leap. We can move in small steps. First of all, you have to be aware of existing problems, challenges, and deficiencies.
I guess
once you understand them, you can make
example
progress.
you're just giving is how do you eat an elephant, one bite at a time? So you kind of have to take baby steps in every sense, and so step by step. One final thing before we wrap up, because we're over time, and well, this will be the last little small question. In terms of just with sustainable energy and saving energy, personally, what things do you do that will actually help save energy? I didn't ask anybody else this, or say, as I said, I saved the best question for last. What do you do to save a little bit of energy?
Oh, that's a good question. Well, actually, I wished I did more. Well, at least I'm aware, and I realize that it must be taken seriously. For instance, waste collection, separate waste collection. This is something that I do. It's a matter of habit, and I think I already have the habit.
Okay,
it's
I guess
working well.
Recycling is always important. Dr. Timothy O'Connor, the Director of the Competence Centre here at the National University of Science and Technology in Missis, and of course, Professor of the Department of Foreign Languages and Communicative Technologies here in Missis as well. Thank you very much for your time today. Okay, and folks, we know that all good things, they do come to an end, and sadly we have come to the end of the forum today. And I hope that you're all coming away with a maybe a deeper understanding or a better understanding of what we can do as individuals to conserve our resources here on this planet Earth. Now today, it couldn't have been possible without the support and the patience and the help of the British Embassy here in Moscow and their cultural sector, because they've been absolutely brilliant in everything they've done with us. All of our speakers, of course, for their time and their patience today and taking time away from their university work and their institutional work, so it's great to have them here as well. My colleagues here at the National University of Science and Technology of Missis, from the Academic University Writing Centre, from my own international office, and from the Office of Marketing and Communications, who've been, they make all these things happen really, really well and make my life easier here on stage. And of course, to all of you for watching and sending in your questions today as well, and your feedback, because it's very, very important to know people are out there and that we are making a bit of an impact as well. That's why we've been hosting these forums. Now, we're going to play out in just a moment with a super short video, a super and a short video, just so to round it off perfectly for today's forum. And I guess we all have to sort of ask a question, as I asked Timothy, what can we do to make a start to try and conserve energy, to save our planet just that little bit better, rather than waiting for someone else to do it. It could be maybe that we're spending a little bit less time on our phone, or on our tablets, or on our computers, or on our laptops, but of course many of us are watching me right now speaking just about that. So on that note, I'll say that I'm Alan Moore, Director of the International Office here at the National University of Science and Technology of Missis. Thanking you one more time and asking that you all take care of yourselves and each other. Until next time, enjoy our video.